Veo a Luis.
Sí, está Luis.
Sí. No, solo vi que se conectó.
¿Dónde está Núñez ahora? ¿Está en Colombia?
Está en Colombia, sí. Oscar. Jairo, Alexis. Carlos.
No, Camilo no está.
Camilo no está. ¿Y Camilo?
No, Camila no está. No.
No está en la reunión. Está en el CERN, yo creo. Está en
Sí,
el
él
CERN, ¿verdad?
tiene un postdoc con España, me parece, pero se queda ahí en el CERN.
¿Qué pasa, amor?
¿Estás en la conferencia?
Sí, pero no he empezado porque no ha llegado la gente. Hubo problemas para la conexión. Mira, 31 participantes apenas. Después de estar esperando como 100, yo no sé qué pasó.
Sí.
Estamos esperando un poquito más para dejar que la gente se conecte. Parece que hay gente que le está costando conectarse.
Es temprano,
Entonces,
es temprano.
esperando un poquito, sí.
Sí, está temprano. Todavía yo soy listo cuando quieres.
Hola a todos, buenos días. Creo que ya podemos empezar. Bueno, bienvenidos a todos y muchas gracias por asistir. Usualmente, pues
right?
Sí, ahora lo hago en inglés, Nico. Usualmente, pues esta reunión la hacemos en presencial, pero bueno, este año no se pudo. Thank you very much, Luciano, for being here and for accepting our invitation. Unfortunately, we could not do this in person, but we hope this week we can have a nice conference. And the main idea is that we share all the work that we do in Colombia, and to have some different scientists invited to tell us something about the work that they do. And of course, it's very special for us to have you join our conference. El programa entonces de la conferencia pues tiene una mezcla de charlas invitadas y de charlas por parte de la comunidad colombiana. Y hoy vamos a empezar entonces con una serie de charlas invitadas especiales, la primera de las cuales es entonces la charla de Luciano Mayani sobre los 50 años del mecanismo JIM. Luego vamos a tener una charla sobre el premio Nobel de este año. Luego una charla sobre teorías Gauge en computación cuántica. Y finalmente una charla sobre el bosón de Higgs, el estatus y los prospectos para el futuro. Entonces creo que vamos a tener una sesión de la mañana muy interesante y que puede ser de mucho interés para todos. Y bueno, bienvenidos al CONHEP de este año, que será virtual. Le voy a dar la palabra a Gabriela, que va a ser la chair de esta primera parte de la sesión. Y nada, nos estamos entonces viendo a lo largo de la semana.
Hello, good morning, good afternoon to everyone, and welcome again to this first session of the 5th Colombian meeting on high energy physics. I have to say that it is a great pleasure for me to present our first speaker, Professor Luciano Mayani. I believe we all know him very well, but let me make a brief summary of his work. Professor Mayani got his first degrees in Rome. He worked at the universities of Florence and Harvard. He was made a professor of theoretical physics at the University of Rome, La Sapienza. He was president of the Istituto Nazionale di Fisica Nucleare of Italy, Director General of the European Center for the Nuclear Research, CERN, President of the National Council for Research in Italy. Here in Latin America, he is also very well known because he was one of the leaders with Veronica Riquer of the programs Helen and ePlanet, which allowed us, the Latin American researchers, to collaborate with European scientists, funding our visits to European laboratories and institutions. Professor Mayani has authored over 100 scientific publications. He predicted the sharp quark in a paper with Glashow and Iliopoulos, known as the JIM mechanism. And today he will talk about the 50 years of the JIM mechanism. So, Luciano.
Gracias. Muchas gracias, Gabriela. Me da mucho gusto de hablar con mis amigos de Colombia. Es una pena que no pudo visitar a Colombia cuando estábamos en el proyecto Helen, pero para los amigos, aspetta un momento. Wait a second. quiero empezar con, let me share my thing. No, wait a second. Share. Okay, can you see that?
Yes.
Yes. So, start again. Para mis amigos de Colombia, quisiera empezar mi charla con algunas fotos del proyecto Helen, en las cuales pienso que habrán algunos que están en la audiencia que puede reconocerse hace algunos años. This is the first picture of Helen when just the day that Helen was approved. And it was very exciting to see a mixture of Europeans and Mexicans. I was in Mexico at the time, and I thought Helen would have been a really exciting project precisely because of the mixing of two different continents. This is a very famous photo that shows Veronica with the first fellows that arrived at CERN. I think there must be some of them in the audience. I'm not sure about the names. And this is the first meeting of with those that we called the Helen kids. I see here Camillo in first line, and many others, very happy faces of people from various countries in Latin America at CERN. This is another one, and you recognize at the end of the table Veronica and Gabriela. And this is still another one. It was very happy. Very nice to have these meetings with young kids from Latin America at CERN in the cafeteria. So let's go to the talk now. This is a picture of a meeting that we did a year ago, almost exactly a year ago, in Shanghai, to recall the 50 years of gene mechanism. You can see here, there is my friend Ong Jan He, but John Ellis, you know him. And then there is Johnny Leopoulos, Shelley Glashow, Veronica, and myself. In fact, you may say that November 2019 was not 50 years of the gene paper, which was published in 1970. However, for me, it was really 50 years because I arrived in Harvard precisely at the beginning of November 69. And there I met for the first time Johnny Leopoulos, which I knew only by his works on paper. And I saw again Shelley Glashow, who had been a professor in my first physics school, which was in Varenna in 1964. So that was the beginning of intense discussions. We were all working in the issue of higher order correction to higher orders in weak interaction. And we did not practically know each other. We started discussing. We had infinite discussions in these months, but after 3 months, we had solved the problem. You may say, I have given a long interview to Luisa Bonolis that has been published in Europhysics Journal Age, that is written here, and here I talk about the whole story. But let me start from the very beginning, late 1960s. At that time, for the first time, it was possible to conceive a unified picture of all the particle interaction. We had quarks, 3 quarks in 3 flavor. There was a very interesting result that up and down quark masses are very small, of the order of MeV, from chiral symmetry breaking. And of course, there was the Cabibbo theory of semi-electronic decays that gave Fermi theory a beautifully symmetric phase. It was current-current interaction, and there was a current for the electron doublet, a current for the muon doublet, and a current for the quark. The quark appeared, the neutral quark, the down quark appeared in the Cabibbo combination with an angle, the Cabibbo angle, and that was it. That was it. All the other fields were singlets. There was a singlet, a weak singlet, the Cabibbo strange quark, the orthogonal combination, and then all the right-handed fields. There were clouds also. There were problems that were standing on our head. For instance, the story of statistics of quarks. Everybody knew that the proton has 3 quarks, but they are in a symmetric state, which seemed to violate Fermi statistic. There were the first ideas about color, but that was really not so clear. What was the basic strong interaction? That had to be an interaction between quarks, not between quarks. And there were one model which circulated, which was a model with an abelian gluon, that is a neutral like the photon. And that was rather familiar, but it was really considered only a toy and not anything else. And then in these years, I'm speaking of 1968 in particular, was the Veneziano model had appeared, and in fact, everybody worked on the Veneziano model. I must say that the 3 people in Harvard that discussed about the weak interaction were almost alone in the world. There was Nicola in Rome, there were a couple of people in Russia, but basically speaking, everybody was working on the Veneziano model. The higher order weak interactions were a problem. Of course, the Fermi theory is not renormalizable. Maybe there is a W boson, but in any case, people did not really worry much, because everybody thought that after all, the 4 factors will dump everything. Of course, there were ideas about unification, but also those were restricted to a very restricted club of people. Glashow paper of 61, SU2+U1, had gone essentially unnoticed. And the Braut-Engler-Higgs mechanism had been discovered in 1965. Again, nobody really paid attention. And however, Weinberg and Salam did. And Weinberg in 67 and Salam in the same time had made a toy model for the leptons, which was exactly the same model as Glashow model, except that Glashow had to put masses by hand, and Weinberg and Salam could use the Higgs mechanism, and could claim with some idea that perhaps this was a renormalizable model like electrodynamics. In 1968, a very surprising result came, and that started the whole business. This really started the business of higher order quick interactions. That was called the G lambda square puzzle. Fermi theory is not renormalizable. You have to work with, even the vector boson is not renormalizable. A massive vector boson is not renormalizable. You have to put a cutoff. And people thought that one line of orientation was to say that the cutoff is at the place where the weak interaction becomes strong. So G lambda square equal 1. That is what everybody expected. But all of a sudden, Joffe and Chabalin made a paper which was discussed at great length in the end of 68 in the Vienna conference, where I was and Cabibbo was as a convener, and that showed that even in a theory with only a charge at W, you have a divergence for the neutral current processes, and you have a divergence for the neutral currents, and the cutoff is in fact very small. So this is the diagram that Joffe and Chabalin consider is a K long which makes two W's, which then materialize into mu plus mu minus, or a K0 which again with emission of two W's become a K0 bar. The amplitudes were found to be divergent as expected of order G times G lambda square, but to comply with the experimental limits, lambda square had to be of order, lambda had to be a cutoff of order 3GeV, which was totally incomprehensible. The result is based on current algebra commutators. So it's a very complicated manipulation of currents. It shows that the hadron Form factors cannot help. The current commutators imply hard constituents. In fact, at the same time, the scaling, Bjorken scaling was discovered in deep inelastic electron scattering. So constituents of hadrons are hard and not damped by form factor. Similar results were found by Marshak and by Francis Lowe. Of course, the papers raised a considerable discussion this time, and the big shot came in, Gelman, Lowe, Kroll, Roderman, etc., suggesting that one could cancel the divergence by introducing a lot of intermediate vector bosons. I think they needed 24 vector bosons, something like that, and that's it. More fancy was a proposal by T.D. Lee and Giancarlo Vic that said that after all, to make the theory renormalizable, you have to introduce a ghost, which is and the lambda is just the mass of the ghost, a negative probability state, which somehow they managed to make it consistent with the quantum mechanics. It was also realized the same year that not G times G lambda square, but really quadratically divergent amplitudes of order G lambda square would arise with potential violations of strong interaction symmetries, parity, isospin, strangeness. And in particular, Bouchard, Leopoulos, and Pranki in the 1968 showed that with chiral SU3 cos SU3 breaking described by a quark mass term, 3-3 bar representation, the leading divergent terms are of the form of a divergence of a current and can be eliminated. Good. Another line, however, was opened by Gatto and collaborators, and then we worked with Nicola on that for 69 on the whole year. That if you asked to cancel the quadratic divergence, but you could find a specific value of the Cabibbo angle that would cancel the divergence, and that was interpreted as a computing the Cabibbo angle, and also that raised a lot of interest, and we spent a lot of time with Cabibbo in Rome working on that. However, the G lambda square divergences may be discussed in this way, but the G times G lambda square term still called for an explanation, the K0 long decay into mu plus mu minus. Here comes the result of our discussion with Glashow and Johnny Leopoulos. As I said, we started discussing in November 1969, and we continued until Christmas. But in January, we had understood. We had found a solution. The solution goes as follows. Well, first of all, during the discussion, speaking many times of these things in front of a blackboard, we arrived to simplify the problem of Joffe. We realized that the problem was in a totally, completely quark diagram. Forget about the kaon, forget about that. The problem was this diagram. This diagram is quadratically divergent, and it has the divergence that Joffe and Chabalin proposed. That was the diagram. And we found a solution in one afternoon. I remember the solution is to add another diagram with a forgotten charm quark, which had already been proposed by Glashow and Bjorken and by many others, as you will see. And in realizing that these two diagrams for massless quarks cancel. In other words, what we proposed was to put the Cabibbo singlet, the strange Cabibbo quark, in a doublet with the new quark, the charm quark, and leave as singlets all the right-handed things. This was a sort of known solution to the lepton quark symmetry. In this case, you see that you have a perfect symmetry between quarks, two doublets, and leptons, two doublets. And the current becomes that. And the miracle of that is that if you make the commutator of this current, which is the coefficient of the GG lambda square term, is the commutator of C times C dagger, and this is diagonal. Has no strangeness violation. The K long does not decay into mu plus mu minus. However, this is not the whole story. The story is more interesting if one keeps the mass of quarks different from zero. So you have these two diagrams, you compute these two diagrams. A gives a certain amplitude, which of course depends from the mass of the U. The C exchange give the same amplitude with MC, but in minus sign because of the alternating Cabibbo D quark and strange quark. And the total is just the difference of these, which is convergent. And in fact, if you compute that, you see that the Joffe-Chabalin cutoff lambda square becomes m square c minus m square u. M square u is totally negligible, as I said, and m square c is the cutoff. The Joffe-Chabalin's result turns into a prediction of the charm quark mass. That was absolutely fantastic. And the mass of the charm quark has to be, say, 1.5 to GeV. That was a very interesting result. And remember that the mass of the up and down quark are about 2 or 3 MeV, and the mass of the strange quark is something like 120 or so MeV in current algebra. But this is a really heavy quark. So charm had to be there, but had to be there with a heavy quark. So we wrote a paper. The paper contains a number of interesting things. First of all, we recognize that it was necessary to depart from the Cabibbo theory. Well, you have to introduce another weak interaction. Then the weak hadronic current has a precise lepton quark symmetry. In fact, the matrix that I showed you before is a 2x2 matrix, and you can convince yourself easily that you cannot introduce phases into that. In other words, you can redefine the fields to eliminate the phase. There is no CP violation in our theory. In contradiction with the conventional three-quark model, the couplings of neutral vector boson has no embarrassment because, as I said, the commutator of the two currents is flavor conserving. Finally, we explained why the search for charm had been unsuccessful until then, because after all, the mass that we found for the charm quark was not so extraordinary. It was 1.5, 2 GeV. So why people have not seen that? We realized that the lightest charmed particle would in any case decay very rapidly, 10 to the minus 15 seconds or so, and would decay in a variety of final states, and it could have been lost easily in the complicated hadronic interaction. But in any case, charmed particles had to be there. They had to be discovered. These were the main messages of our paper. There was a problem that was not posed very much at the time, but in any case is relevant. And one might suspect that the strong interaction will spoil the cancellations at the basis of GeM, this cancellation between the up quark and the charm quark contribution. But there was a paper already written a few years before by Preparati and Weisberger that said that the relations of the weak interaction connected to the commutator, algebra commutators, are preserved by strong interaction if this strong interaction, so to say, commute with the vector interaction. In other words, they are mediated by one neutral or more neutral gluons. As I said, this model was considered essentially a toy model, just something that could mimic the interaction between quarks. In particular, if quarks had if the charge to which the neutral gluon is coupled does not commute with the electric charges of the quarks, then it would not work. We did not worry much about that, but it's very cool, it's very interesting that a few years later, the theory of strong interaction, which now we call QCD, is in fact based on 8 electrically neutral gluons. And this is why the GeM relations survive without renormalization. In other words, the strong interactions in leading order renormalize the quark electroweak parameters, masses, engaged coupling, the strength of non-leptonic process, etc., but don't touch the basic symmetries of the electroweak that are generated in the 4-quark model. By the end of January, as I said, we thought we had understood everything. In fact, the paper was written at the time. And I remember that one day we usually went to a seafood restaurant for lunch many times. My wife joined us, and Pucci said to Shelley that I was very happy and excited for the result. And Shelley candidly said, yes, he is right. This paper is going to be on all school books. I was very surprised, but okay. And Shelley, in fact, was very excited of this result, and he gave a seminar to the experimentalists in Harvard that worked the Cambridge Electron Accelerator, and the opening was this: look, guys, we have essentially solved particle physics. Pause, except for CP violation. I think he was absolutely right, and it was very, very interesting. What happened following GeM? But apart from charm, the main prediction of GeM was that the neutral current semi-leptonic process must exist. Because, of course, they must exist mediated by a flavor non-changing current. So the charmed particle in particular had to be produced in pairs. but in any case, the neutral current semi-leptonic process are predicted. And in 1973, it was very rewarding that Gargamel bubble chamber collaboration at CERN observed what they called muonless or electronless neutrino events. And they were soon recognized to be neutrino process of the type neutrino plus nucleus that gives neutrino plus hadrons. And our prediction was that the hadrons could contain charged particles, but only in pairs. In fact, practically the year after or so, this prediction was supported by the so-called dimuon events, events in which there were two muons in the final states, which were interpreted as a pair production of pairs of charged particles. The quark-lepton symmetry was one of the elements of our paper, and 2 years later, 1972, in a paper by the usual French collaboration, Bouchard, Liopoulos, and Meyer, they found that this quark-lepton symmetry is mandatory for a unified electroweak theory for the cancellation of the other Bell-Jacob anomalies. I remember John wrote me a letter, very excited, by saying charge must exist and SU3 and quarks are fractionally charged. We were just at the beginning of the period where QCD was discovered. CP violation was not there with 4 quarks. I must say that we were already worried that our prediction of another quark had to be verified, etc. We did not ask what would happen with even more quarks, and so failed to discover a simple theory of CP violation. In fact, I rediscovered it in '76 after the tau was discovered, and was reminded soon that 2 Japanese fellows had already written the CP violation with 3 doublets already in 1973. So unified theory of quarks, as I said before, if you take the Kabibel matrix and make the commutator, you get a diagonal, fully diagonal matrix, which is this C3. C3 and Q are coupled to 2 vector bosons, which are linear combination of the photon and the Z0, and there is no problem with flavor changing currents in extending the Glashow-Weinberg-Salam theory to the hadrons. The G mechanism makes it happening. Of course, the flavor changing neutral current arise to order, as we have seen, G times G MC square, and there was a very interesting calculation by Marie-Kay Gaillard and Ben Lee in 1974, in which they computed all these diagrams, now in a really unified electroweak theory, and again came out with a number from the experimental limits on this amplitude, came out with a number for the charm quark mass, which was more or less the same that we had envisaged in 1970. I want just say a few words in CP violation. As I said, the CP violation with 3 left-handed quark doublets had been described by Kobayashi and Mascawa in 1973. In 1976, there were 2 papers. One was Pakwaze Sugawara, and the other was by myself, analyzing the CP violation in KDKs and showing that this phase could explain the observed CP violation in KDKs. I added the observation that the neutron electric dipole vanished at 1 loop. In fact, the Russians added that it will vanish also at 2 loop, and so in the standard theory, the neutron electric dipole is predicted to be extremely small. It has never been observed until now. There are only upper bounds. Bigi and Sanda predicted the CP violation in BD case. And as you know, that was discovered in 2001 by Bell and Babar in BD case. And now we have the full Kabibo-Kobayashi-Maskawa matrix, which is written here in the so-called Wolfenstein parametrization. And you know that this is in perfect agreement with the experimental data. It is interesting that, in fact, charm had been predicted before, more or less for this reason of universality. Before quarks, elementary particles were described in the Sakata model using proton, neutron, and lambda as basic baryons, and neutrino share between electron and muon. And after the discovery of two neutrinos, Sakata et al. Proposed to extend the model to a fourth baryon called V+. As you noticed, this is on the same line as the proton, and the proton and V+ have the same role as up and down, as up and charm quark, and neutron and lambda the same role as down and strange quark. So you have again perfect symmetry between quarks, between sakatons and leptons. And as I mentioned in '64, Glashow and Bjorken proposed a similar model for the quarks, invented the name charm, and but they thought that the charm quark was related to the constituents of the phi 1GeV. This is what Shelley lectured in Varenna in 1964 with the observation that that was already excluded by the experimental data. In fact, in 1971, New and collaborator observed in the collisions made in emulsion by cosmic rays, emulsion in high altitude, and they observed kinks, you see here, that signal a decay in flight. And this is another one, this is another one. And these kinks were interpreted as the production of unstable particle, which decays in, roughly speaking, 10 to the minus 13 seconds. And in fact, the Japanese, thinking to the Sakata idea, had analyzed this as the claim that these events were the discovery of charm, which is, I think, correct. But nobody paid attention to kinks in emulsions in Japan, in the Western countries. They simply were not considered. And we had to arrive to 1974 when Ting and Richter discovered the J-psi, which, as you know, is the first example of a bound charm-anti-charm. And then in 1976, in SLAC, the D0 meson was discovered, 1865 MeV, and shown to decay weakly, etc. And that was the registration of charm discovery definitively. I have here, the same year, Lederman and collaborator discovered the Upsilon PBR family, a first evidence of the third family. So 1976 was a crucial year because the B was seen and the tau was also seen. So the evidence for a third family came together with the evidence of charm quark. I have this beautiful picture of the hydrogen bubble chamber, a neutrino reaction, which shows the complication of the decay of a charged particle. And let me, you can follow here. The reaction is neutrino proton, which gives the star proton mu minus. So you have the proton and the mu minus are these particles that are the most energetic one. Then the D0 decays into K pi, and the K pi are this and that, Pi is very high energy because the mass of the D is large respect to the kaon and pion mass, but however the D star decays into the 0 plus a very low energy pi plus, and you see here this pi plus here. This is the low energy one that decays in mu, and then the mu finally decays into the electron that spiralizes into the magnetic field as a very small energy. The K is seen to stop in the bubble chamber, but with the proton, it gives rise to a sigma minus pi plus. Here is the pi plus, and the sigma minus decay into neutron pi minus. Here is the pi minus. And where is the neutron? The neutron is here. You see a kink, a proton which is kicked by the neutron, and that is the revelation of a neutron. So it's a magnificent picture that also tells you how complicated it is to see the decay of a charge particle. Now, what is the meaning? The meaning we don't know. What is the meaning of the fact that the quark is heavy? But we know how a heavy quark behaves in QCD. The heavy quark, for instance, decays in many, as we have seen, in many channels in semi-leptonic decays, and you can treat the final state as you do in deep inelastic scattering. That's the message. The mass is much larger than lambda QCD. The decay of a charged particle is like deep inelastic scattering. In 1979, with Nicola Cabibbo, we computed the inclusive charge decay, and we compare that to the experimental data, say for the decay, etc. And you see that the result is very interesting. These are modern data, 2010 Cleo. And you can also introduce gluon correction, as you do in deep inelastic scattering, and the thing go well also for BDK. The other fact that is related to the heaviness of a quark, I'm about to finish, is the fact that it's difficult for forces inside the hadron to create or destroy a CC bar pair. If a CC bar pair is there, it is difficult to disappear because it has to annihilate at very short distance where strong interactions are very feeble. So a hadron with a CC bar or a BB bar pair and electrically charged particle pairs must contain additional light quarks. Realizing the hypothesis that was done by Gell-Mann in the very beginning, when he said that baryons can be constructed from 3 quarks or perhaps 4 quarks and an antiquark, and mesons are out of QQ bar or perhaps two pairs. We call now, for short, we call this combination pentaquark and this combination tetraquark for obvious reasons. And now, the fact is that this particle has been observed because there are new valence quark configuration. And the first charged configuration, which contain a CC bar pair, is the so-called ZC4430, was discovered by Bell, and decays into a J psi, so it has to contain a CC bar pair and pi plus, and so it has to contain 4 quarks in various combinations. And that's a long story that was solved by LHCb that made a very high statistics, high precision study, and showed that in fact it is a really school books resonance. Then Best 3 in Beijing discovered two other particles of this family. One is 3900 mass, it's called Zeta C, and the other is Zeta C prime, 4020. They are very close to each each other, and this decay into J psi plus pi plus, and this decays into HC, which is again a harmonium particle plus pi plus. And then more recently, in the spectrum of K of in the spectrum of psi proton, LHCb discovered lines which is interpreted as a line which has 5 quarks, because there are a CC bar pair in psi and 3 quarks in the proton. There is no consensus yet of how these quarks are organized inside the hadrons that we see. There is something that they are made what is called a hadron molecule, that these 2 colored singlets bound by nuclear forces. We in Rome studied in all details the compact diquark anti-diquark model, diquark and anti-diquark bound by QCD forces. And then there are other more fancy model which envisage a nucleus, a harmonium nucleus, which then is neutralized by a cloud of light quarks. If you want to know more about that, we wrote recently a book on all this subject, which is very interesting, and I take the occasion to make a small commercial. The new sensation is with 2 heavy baryons in a tetraquark. The structure is like that. This was hypothesized by several people, and the real glamour is that Karliner and Rosner, Eichten and Quigg computed the mass of these states for a pair of charm and a pair of light quarks, or a pair of beauty and a pair of light quarks, and found that the Q value, that is the difference between its mass and the mass of a BB state, plus eventually a photon, is negative. So this double B should decay only weakly. And with Antonello Polosa and Veronica Riquer, we made a first principle calculation in the Born-Oppenheimer approximation and found the same result. And a very similar result is also found on lattice calculation. So I think that there is a clear prediction that the 2 beauty tetraquarks will be stable under the weak interaction. This problem has been studied by Ali and collaborator, that showed that if you have, say, 1 giga Z zeros, that is 10 to the 9 Z0, you could have a sample of 1,000 of these decays. This would be, this tetraquark would have a spectacular decays like J psi and B minus and K0, etc. So you could see events in which you see 2 kinks or 2 vertices at large distance. If you produce here this TBB U bar D, you have a first in which this decay into a J psi plus a B minus, and then later on the B minus also have another weak decay. So 2 weak decays in cascade. That would be very spectacular and a new territory for experiments, but also for non-perturbative methods in QCD. Finally, last June, LHCb has observed resonances in the pair of J psi particles. Resonance with the pair which decay into a pair of J psi. There are little doubts that these resonances are tetraquarks. That is, they are states done like that. 2C and 2 anti-C bound together by the QCD forces. You can study the system, it's very interesting. Fermi statistics says that it has to have spin 1, so it will decay into into 2 J psi with J equals 0, 2 J psi with J equals 2, etc. we have studied that is again a new avenue for the future. I want to conclude this with giving you now the vision of the constituent and fundamental forces that we have now. This is what is called the standard theorem, the standard theory. This is Gell-Mann that introduced up and down quarks. Cabibbo introduced, no, Gell-Mann introduced also up, down, and strange, but Cabibbo introduced the universal weak coupling for strange, and we introduced the charm doublet, and Kobayashi and Mascala introduced the third doublet. Shell, Glashow, Weinberg, and Salam introduced the SU2 cross U1 intermediator, and Carlo Rubbia is the one that discovered the Z and the W. And the gluon is the mediator of strong interaction between quarks and is responsible for strong interaction which are asymptotically free. It's a beautiful, beautiful scheme, which is completed by the Higgs mechanism and then the Higgs boson, the last discovery of our discipline. You see here in the historical day, 4th of July 2012, you see here Robert Engler and Peter Higgs discussing in the room where the discovery of the Higgs boson had been announced. And finally, this is what we have now. Everybody is looking for what is beyond the standard theory, but also within the standard theory, there are things that we do not understand, and we will have to search for it. So let me conclude. It's been a real pleasure to come back, to come to you with my own memories. Gym mechanism is alive and well. It is an efficient tool for searching for flavor changing processes. The heavy quarks are a good indicators of the dynamics of hadron spectroscopy, and I gave you two possible subjects for the future: weakly decaying doubly heavy tetraquarks and fully charged tetraquarks and fully bottomed tetraquarks, amenable to a theoretical description, perhaps a second channel. Thank you.
Thank you very much for this wonderful talk.
Thank you.
Yeah, we are very happy with your talk. So now, questions, please raise your hand in Zoom and we will let you ask the question. Questions, please.
Oops. Oh, sorry. Okay, questions?
I don't see any, so maybe I can start. So Luciano, you know, we are now with the LHC, but there are many different experiments that are being thought for the future. And yes, we know about the other accelerator at CERN and in China and many other options. So what do you think about the future of our experiments in high energy physics?
Well, what is the future? Well, there are two different. First of all, I think that the future is in yet another generation of accelerators. And I think that the line which is emerging both in Europe and also in other parts of the world is to make a circular Higgs factory that is a very big, really big tunnel, say 100 kilometers circumference, put there an electron positron machine, and then which would be a Tera Z factory also in addition to a Higgs factory. And then eventually, if there are indications for new physics at high energy, then go to the same strategy of the LHC, that is replace or add in the same tunnel to the electron-positron machine a proton machine of, say, 100 TeV. I think that this strategy is essentially determined, and I would concur with that. What I think is the discovery of these years is that at the level of the Higgs factory or Z factory, super, you will find you will have not only the possibility to look for deviations of the Higgs property from the standard theory, which then would signal another physics at high energy, but you also can study these exotic hadrons, which are at the limit of visibility with the LHC. LHC can produce them, but certainly with a lot of noise and not with enough cross-section because of the energy limitation. And certainly a Tera Z factory would produce these tetraquarks that have been discussing in great abundance and can tell us a lot of things about the strong interaction. So I think this is very, very interesting. Of course, waiting for the machine of the future, I think that LHCb is very well placed for studying this kind of hadrons, but also I think that ATLAS and CMS should dedicate some time to this physics. It's no good to be only along the side of beyond the standard model. This is interesting physics, and I think that CMS and ATLAS can contribute to that.
Sure. Yeah, sure. Okay, more questions for Luciano? You can write in the chat if you want. Here. Let's see. Okay, let's see if someone has a question. You can write it in the chat and we can read it if you want.
Well,
I don't see any. Maybe I can make another question.
Sure.
And what about the theoretical physics? What do you know? What do you think are the challenges now in theoretical physics? Because, you know, now we are trying to find something in the LHC, but it looks like it's it's not appearing yet. We hope we can find something, but anyway. So what do you think about the challenges in theoretical physics?
Well, you see, theoretical physics is in a strange way. I mean, many things have been said, and unless there is something really new, I mean, the world is to the experiments. We have to know what is at large energy, and without that, I don't think we will be able to, or at least it's possible, but it's not so clear that you can devise between the various things. What is the dark matter? Is that really supersymmetric particles or axion, etc.? Well, until there is an exploration of the really high energy side of the standard theory, that is until, say, 10 TeV in mass, etc., it will be very difficult to say anything about that. This is, in a way, also the importance of these things that I've been telling you. In other words, there are new phenomena, there are descriptions, there the theory can work to find, for instance, a theoretical description of the tetraquarks or of the double heavy tetraquarks or pentaquarks, etc. So there is work to do. Now, where this work will lead, it's difficult to say at the moment, but I think that physics is like that. You have interesting phenomena, you would like to understand them better, to have a theory. Possibly from this theory, new ideas will come for the future. So there are these two roads. One is to to go to really high energy. The other is to study what we have at the moment. And both are interesting and both have to be done. Both point out to the need of a Higgs-like factory or Zeta-like factory, better if it is in some place where you can extend to a really high energy proton decay. For the theory, we are in a way similar to what happened in the past. The theory is waiting for illumination from the experiment.
Sure, thank you. Well, we have a question here in the chat. So Jose Munoz is asking, what was the principal conceptual difficulty to propose the gene mechanism?
No difficulty. You had to think about it. In other words, you speak about the gene mechanism?
Yeah.
That was the question. No difficulty. Simply, people accepted some prejudice that there had to be only 3 quarks, and that was a real prejudice. I mean, the advantage of our paper was to show that if you get another quark, everything becomes simple, and there was no mathematical difficulty to discover it. It was all written in those very simple Feynman diagrams that I showed you. And of course, we made a lot of calculations. You can imagine that. We made a lot of calculations. How are the G lambda square divergences organized, etc. You make always a lot of calculation to understand the surrounding. But the real fact is that people accepted 3 quarks blindly. That was the idea. And once you have Joffrin-Chamberlain and for quarks, you put the 2 things together, and the mathematics is very elementary.
Thank you, Luciano. More questions for Luciano?
I have a question. Thanks, Luciano, for this super nice talk. You just mentioned about supersymmetry, so I was curious about your opinion on supersymmetry, and in particular, when should we give up on SUSY models?
But look, supersymmetry is a wonderful idea. People say that supersymmetry is dead, but I don't think so, because supersymmetry, I mean, the hierarchy problem tells you that the supersymmetric particle must be close. How close? You don't know. You don't have a I mean, in charm, there was a number that said that the charm quark mass had to be, say, less than 2 GeV. So that tells you that things have to be found there. Now, for supersymmetry, somebody says that the mass difference must be of the order of 1 TeV, but of the order of 1 TeV. It could be 2 TeV, 3 TeV, 4 TeV, 10 TeV, sort of. So supersymmetry is essentially untested, and will remain untested with the LHC. You need to go to higher energy. This is my opinion, and of course there is the difficulty that underground experiments do not see any signal up to very small cross sections, etc. But again, if the mass becomes larger, then these limits are obeyed. So I don't know. I think really we need inspiration for the experiments at higher energy to do that.
Okay, thank you very much.
Okay, there is another question here in the chat. Regarding the final comment on BSM, in your opinion, what would be the most urgent questions to address within the standard model?
Within the standard model, there are no urgent questions. Well, perhaps the most urgent question within the standard model is the mass of the neutrino. Is the neutrino Majorana, or that is under the chapter double neutrinoless double beta decay. And that is something that we hope will be found in not too distant future. Limits are going down, and we hope that we will know that. That would be a really important thing to get inside the standard theory, which does not require any particularly dramatic extension. That also will solve, maybe will solve the asymmetry or baryonic asymmetry in cosmology. But as I said before, in theory, there is nothing within the standard theory except for the low energy strong interaction that we do not know how to solve. So the mass of the neutrino and the strong interaction.
Okay, thank you. More questions for Luciano? I don't see any hands. I don't see anything else in the chat. Okay, thank you, Luciano, for your wonderful talk. Thank you very much.
Thank you all. Thank you all. Bye-bye. Have a nice time.
Thank you. Thank you. Thank you. Thank you. Okay, so now our next speaker is Jessica. Jessica received, Jessica, are you, I'm going, someone can try to give her permissions to share. Let me see where is Jessica.
Gabriela, would you make me host? I can do that.
Okay, good. Mario, where are you? Mario. Mario. I don't see you, Mario. Here. Yeah, I saw you. So now you are the host.
All right, thank you. I think it is ready for Jessica to share, to be able to share.
Okay, yeah. Now, great, good, perfect. Okay, so let me introduce Jessica Liu. Jessica received her undergraduate degree in physics from MIT in 2000 and her master degree in astrophysics from UCLA in 2005 under the supervision of Andrea Guess. Of course, 2020 Nobel Prize awarded. Jessica was granted her PhD in astronomy and astrophysics at UCLA in 2008. Her doctoral thesis studied the origins of young stars in our galaxy's central parsec with stellar dynamics. After she finished the PhD, she was awarded a Millikan postdoctoral fellowship in observational astronomy at Caltech. She was also an NSF astronomy and astrophysics postdoctoral fellow at the Institute for Astronomy in the University of Hawaii, Manoa. And currently, she is an associate professor at the University of California, Berkeley. Her group searches for black holes in the Milky Way using photometric and astrometric micro lensing. Today, she will talk about black holes in the Milky Way. So, Jessica.
Thank you. Can you hear me okay, Gabrielle? Okay, great. Thanks so much for the invitation. I really appreciate the opportunity to come and talk to you, especially in this auspicious year. Black holes, astrophysical black holes in the Milky Way in particular are quite a fun topic to talk about. So I'll go through about 45 minutes of presentation, and then I'm happy to take questions. But if you'd like to interrupt along the way, I'm happy to do that too. I cannot see the chat though, unfortunately. So you'll have to pipe up with your questions or someone can relay them. Okay, so first off, much of this work is done in a huge collaboration. Let's see if I can change my slides one moment. Yeah, there we go. Of course, I work with a large team called the Galactic Center Group at UCLA and Berkeley now and Caltech, and we use the Keck telescopes to study black holes across the Milky Way, both large and small. So let's start from the beginning and basic concepts and talk about what is a black hole. A black hole is really a quite simple phenomenon. It's an object that is so massive that the density, gravity wins and the density goes to infinity. And in physics, we fundamentally call this a singularity. It's a breakdown of our fundamental physics. So black holes are always going to be intriguing until we have some theoretical explanation for them. And in the meantime, we try to observe them experimentally early on, prove that they existed, where they're found, and what their basic properties are. I'll be focusing on black holes that are of an astrophysical origin, and we think they are extremely simple with just two basic properties, mass and spin. For astrophysical black holes, we won't be talking much about charge. We just simply don't think that there could be charged black holes running around the universe. So black holes in the universe come in a couple of different varieties. First, there's what we call the ordinary black holes. This is at the fate of a massive star, something more massive than 20 or 30 solar masses. When it dies, it reaches the end of its life and it's fused its core all the way up to iron or nickel. The fusion pressure, the fusion generated energy is no longer sufficient to hold up the star. Fusion becomes endothermic and instead of exothermic, and you have a collapse. And at that point, the collapse, there's no other form of degeneracy pressure or quantum pressure that we know of that can hold up the object, and you form a black hole. These massive stars, we think, turn into black holes of about more massive than 3 solar masses. 3, maybe up to 80 solar masses. So much more massive than the sun, but still not the most massive black holes in the universe. The second type of, these black holes were first predicted by theory as a consequence of general relativity and have since been confirmed as existing in the Milky Way and in nearby galaxies primarily through accretion of X-ray binaries, black holes accreting mass from a companion star, and more recently by LIGO and the detection of gravitational waves from black holes as they merge. So we think in our Milky Way, there may be as many as 1 billion of these stellar mass black holes flying around, somewhere between 100 million and 1 billion, and we simply don't even know that number to better than an order of magnitude. The second variety of black holes, which I'll focus on mostly today, is the supermassive black holes. These are much more massive, 1 million to 1 billion solar masses. We really don't have a good idea of how they've grown since the beginning of the universe. We think that galaxies have one at their center in almost all galaxies. We do think they are ubiquitous throughout the universe, and they've been detected in present-day galaxies all the way back to galaxies in the early universe. And these black holes were first suggested by observation, not by theory. And so it's quite remarkable that they exist in the first place, and proving that a supermassive black hole was there at the center of our own galaxy was the subject of this year's Nobel Prize. The third I won't talk too much about, but there's a small chance that there are also something called primordial black holes that grew during the inflationary expansion of the universe through local overdensities in space-time. You can get a small black hole to exist. These are incredibly speculative. Theoretically, they're very popular as a potential component of dark matter, but we know almost nothing about them because they've never been detected. We don't even know if they exist. Okay, so how do we find black holes? I've told you about their categories, but really 25 years ago, how did we know that they existed? How did we find them? In particular, how do we find black holes in our own Milky Way? And I'll focus on this first part on the supermassive black hole at the center of our own Milky Way galaxy. As I mentioned, this was the subject of half of the Nobel Prize this year for Reinhard Genzel, who leads a group studying the supermassive black hole at the center of our galaxy. in Germany using the Very Large Telescopes, VLT, in Chile. And my own work with Andrea Ghez, who was awarded the Nobel Prize. We work with a group, a large group that uses the Keck telescopes in Hawaii. And we are primarily located in University of California at Los Angeles and Berkeley and Hawaii and Caltech. So the galactic center, this is what you would go out and see of the galactic center if you went out at night and could dark adapt and look for a very long time, integrate for a long time with your eyes. And it's almost hard to find where the galactic center is in this photo. And that's because we're looking at our galaxy edge on. It's a disk galaxy, and the dust and gas absorbs 1 out of, or almost 10 billion of photons that are coming to us. Only 1 out of every 10 billion makes it to our eyes and to our telescopes. So that dust obscuration of the optical light makes the galactic center incredibly difficult to find in the first place, much less search for a supermassive black hole there. Fortunately, in the last 50 years or so, we've developed the capacity to see light at other wavelengths in the radio and the X-rays, and for this talk, most importantly, in the infrared. And at infrared wavelengths, we can peer past the dust and gas. And now 1 out of every 10 photons makes it to our telescopes of infrared light. So infrared astronomy was really the key development in order to study the center of our galaxy, but it was not the only key piece of technology. So if we look at our galaxy at infrared wavelengths and we zoom in here, you can see how crowded the center of the galaxy is. So there was certainly a peak in infrared light, but that peak was not a single star or a set of stars that were resolvable. It was a big fuzzy blob. These are images taken with the 2-mass telescope, which is a small ground-based telescope. And you can see there's just simply not enough spatial resolution to see individual stars and find a black hole, a supermassive black hole, if it did exist at the galactic center. So certainly we need a better spatial resolution. To get sharper images, we need a bigger telescope, a bigger optic. And this is where the Keck telescopes come in. The Keck telescopes are a pair of twin 10-meter telescopes located on the summit of Mauna Kea in Hawaii. And each of these telescopes, in principle, could produce far more detailed images, but in practice, they were limited by the fact that they're still on the ground, and the very air that we breathe causes the stars to twinkle and to blur, and unfortunately does not produce better spatial resolution than even the 2-mass telescope images that I saw before, at least not without some tricks. So this is where the story began in the mid-90s. My PhD advisor, Andrea Ghez, along with Eric Becklin, who is on the left, and Mark Morris, who's next over. Andrea's in the middle, and her first graduate student, Beth Klein, is on the right. They worked with an instrument builder, Keith Matthews at Caltech, to build a special instrument that would take fast pictures of the stars. They would take 1 picture every millisecond and freeze the atmospheric turbulence so that you could get a diffraction limited image with the telescope. This instrument was deployed at Keck, and it was used to take the first infrared pictures of the galactic center with a large telescope, an 8 to 10 meter class telescope. And in the middle is a single one of these individual 1 millisecond frames. This is actually, you see, it's the blurring of the stars is evident as a speckle pattern of sort of individual, what looks like many stars, but it's actually 1 star that's been scattered around by the Earth's atmosphere. And if you take thousands of these millisecond exposures, each one is in principle diffraction limited, and you can shift them and stack them and add them together and produce the high resolution image you see on the left, which is a fairly small field of view image. And if you zoom in on that, you can see individual stars, which now we know is where the black hole is located. But at the time, it wasn't clear where in this picture the black hole would be. So these early measurements amounted to taking pictures. In this picture that I showed here, this was a time period where you took data and you could not see the pictures in real time. You had to save them to disk and then go back down the mountain and process them the next day. It took a huge amount of computational power to go from this image that's on the right to the image that's on the left here, and produce the high resolution deep image to see the individual stars. So it amounted to taking these pictures and measuring the positions of stars as precisely as possible. And then you see over the course of the first 3 years of the experiment, on the right, the positions of the stars were moving in a detectable fashion, moving by quite a bit. You can see some of those stars are moving from year to year by almost more than a resolution element of the telescope. So this was the beginning, and they were in business. They knew that the stars were moving fast enough that probably something was in the middle. And so in the early days, the first results came just by looking at the velocities or proper motions of the stars. Using those velocities, you could infer what kind of mass had to be in the middle of those stars to make them move so fast. So this is a plot from the earliest papers on the galactic center at infrared wavelengths, showing enclosed mass on the vertical axis and the radius at which the stars were, the projected radius at which the stars were on the horizontal axis. And you could see already in these early days, in the late 90s, there were indications from these stars that they were, that the enclosed mass, there had to be at least 1 million solar masses of material, and there were certainly not 1 million solar masses in stars detected. So this dark mass was present and detectable just from the motions of stars. Now, the dark mass didn't necessarily have to be a black hole at this point. It could have been a small cluster of black holes. It could have been a cluster of brown dwarfs or some other dark objects that just didn't have luminosity, that were sort of more vanilla, stellar in nature. So then the race was on to march ever inward and figure out how packed in this mass had to be, and to increase the constraints on the density of that mass. So if you could confine this few million solar masses to smaller and smaller volumes, eventually you can rule out all other possibilities. Measurements continued into the early 2000s using this speckle technique that I mentioned. And then just with time, the star's motions showed that they began to curve. These accelerations could be measured, as you can see on the left. There was one star in particular called SO2 or S2 that was showing very high velocities and a lot of curvature. And at the time, the orbits were not certain. The red lines that you can see were the range of orbits that were allowed in these early 2000s papers. And the enclosed mass was still at 1 million solar masses, but now we were a factor of 2 or 3 further in radius, able to confine that mass to smaller and smaller volumes. Now, this speckle technique was always challenging. And here's a picture of, if you take these fast frame images, what you see. Let me see if I can start the animation. There we go. So this is pictures of a single bright star through the Earth's atmosphere, but taking an image every millisecond. So this is the speckle cloud that you can see. And as I said, you have to take thousands of these images and you throw lots of them away. So the sensitivity and precision and signal to noise ratio of this data from this technique is very low. And around the 2000s was when the first adaptive optics technologies started to be installed on the world's largest ground-based telescopes. Now, adaptive optics is a real-time way of correcting the Earth's turbulence. And it's quite an interesting technique, so I'll show you a little bit about it. The waveforms of light that are coming in from the top of the atmosphere are undistorted. They experience turbulence as they move down through the layers of the Earth's atmosphere and become distorted wavefronts by the time they reach our telescope. The way adaptive optics works is you use a known bright star, a bright isolated star. It has to be visible in the optical wavelengths, and you send it to what's called a wavefront sensor camera, a very fast camera that's taking pictures and measuring the deformations, the aberrations of this wavefront. And then the really key technology here is that there is a deformable mirror that can then shape, undistort the wavefront and shape itself on millisecond timescales. So this is a small mirror, about 10 centimeters in size, and it's moving with actuators behind it. It's a very thin mirror with actuators behind it, poking it and deforming the mirror once a millisecond. So if you can measure and correct fast enough, you can remove the blurring effects of the Earth's atmosphere. This technology was originally developed for military applications, but then was released to astronomers for public use for science and research purposes. And it was really essential for use in observing the galactic center. Now, there was one small limitation to this technology for galactic center observations. It required a bright optical natural guide star, at least initially, to make this wavefront measurement and apply the correction. And so at the galactic center, as I showed you before, what would we use as an optical guide star? There's no really bright optical guide stars visible. We didn't have one. So instead, what we used was a laser guide star. So this is the technique of creating your own fake guide star using a sodium laser that we shine up into the Earth's atmosphere. We tune it to excite a layer of neutral sodium atoms that are about 90 kilometers up in the atmosphere. This neutral sodium, the sodium in our atmosphere, is deposited by micrometeorites constantly bombarding and raining on the Earth. And the sodium that those meteorites deposit rains down, and as it reaches 90 kilometers, it's the temperatures and densities are such that it's neutral. So we can illuminate that sodium layer, excite the sodium atoms, they will decay and emit, producing a fake guide star. And we can use this laser guide star to measure our wavefront aberrations and correct them with our deformable mirror. So let me show you what this looks like in practice. This is a seeing limited picture, a blurry standard picture we would get with a large ground-based telescope with no speckle imaging, no adaptive optics. This is the galactic center. If we turn on our adaptive optics system, in real time, we can suddenly take images that look like this. So the difference is quite remarkable. And the first time we got onto the telescope with adaptive optics, it was just astonishing. Suddenly we could see in real time immediately what was going on at the galactic center. Laser guide star observations of the galactic center also enabled us for the first time to take spectroscopy at the galactic center, which we were not able to do before with speckle techniques. And so the very first spectra were taken of that star SO2 as it was moving around the black hole. It was discovered that it's a hot young star, apparently young star, which is really interesting in itself. What is a young star, only maybe 5-10 million years old? What is it doing so close to a supermassive black hole? But more importantly, the absorption lines in the spectra allowed us to see and measure the radial velocities, the line of sight velocity of the star, in addition to its motion on the sky. This, for the first time, allowed us to measure three-dimensional orbits. So watching the motion on the sky for long periods of time and the radial velocities. And that allowed us to see that everything was moving and really tighten up the constraints on the enclosed mass. You can see in yellow is that star SO2 or S2. And the solid line, when it goes from dash to solid, is where we started taking radial velocities. So in the mid-2000s, this was when we first started to be able to take these spectra and radial velocities, and with the combined line of sight velocities and the motions on the sky, we were able to show that the closest star came within 45 astronomical units. That's basically a Sun-Pluto distance of the mass. And that they were moving fast at closest approach. They were moving 12,000 kilometers per second. And that the enclosed mass had to be about 4 million times the mass of the sun within that volume. And at that point, there's nothing that is allowed except for a supermassive black hole at those matter densities. So this was really fundamentally, these three-dimensional orbits was really the first time we could show that this amount of mass, that this enclosed in this volume existed at the center of our own Milky Way, and that we indeed had a supermassive black hole. So these were exciting times. There were the two teams were working to discover the black hole. Here we are at a conference. These are members of both of those teams. You can see Andrea Ghez in the right, in the middle on the right, and I'm sitting across from her, and Eric Becklin and Tuan Do and Andreas Eckart. Unfortunately, Genzel wasn't at this table for this conference. Otherwise, it'd be nice to have a picture of us all together. But at these conferences, with these images, we were talking about the black hole, its mass, its distance, and whether it was a black hole. But we were also discovering so many new questions to ask about the galactic center. Really, thanks to laser guide star adaptive optics. Here's a picture of us using both Keck telescopes at the same time, pointed towards the galactic center. We started to discover things that we didn't even anticipate asking when this experiment first began in the mid-1990s. In particular, we knew where the black hole was because of the motions of the stars, and we could see now in real time what was happening at the galactic center. So one night we were taking observations, and we noticed that one of the stars was flickering. Let's see if I can turn that on again. Oh, sorry. There we go. And you see also that when we started to be able to take color images at multiple wavelengths at once, there was an object that was both flickering and very red. And it turned out to be exactly at the position of the supermassive black hole. And in fact, this was evidence for gas accreting onto the supermassive black hole and producing non-thermal emission that we could see as flickering in the infrared as different amounts of mass fell in. This has been extremely interesting to probe the accretion flow onto the black hole, so the gas material that's falling in through the event horizon. And now the supermassive black hole at the center of our galaxy is being studied through its infrared emission, its X-ray emission, and its submillimeter emission, often simultaneously. So these experiments are ongoing and help us to understand how gas is feeding the black hole today. In particular, our own black hole is very underluminous, so it's not clear why it's eating so much material but not producing very much emission. You can see it's not much brighter than the surrounding stars. So that was one very interesting discovery along the way, and still an area of active research today. On the gravitational potential front, we've continued monitoring the stars as they orbit around the supermassive black hole. In particular, we anticipated that in 2018, that star SO2 would go through its closest approach. And it approaches so close to the black hole and is moving so fast, it offered an opportunity to make the very first tests of relativity, general relativity in particular, around a supermassive black hole. As I mentioned before, supermassive or black holes in general are singularities. They're a point where our current understanding of fundamental physics breaks down. And we don't understand them. So there are many, many proposals for how gravity theories can be modified to accommodate the quantum mechanical regime and merging gravity and or general relativity and quantum mechanics together. And some of those entail general relativity breaking down around supermassive black holes and modifying general relativity in that domain. So this was a very interesting experiment that we could do by studying the galactic center. It's a different kind of general relativity experiment or test compared to what we can do in our own solar system, where we just are restricted to a small mass, low mass, one solar mass star. So the idea in 2018 was to watch SO2 as it went through its closest approach and look for its gravitational redshift, look for the change of the color of the star or the redshifting of its absorption lines in spectroscopy. But to do this experiment properly, you really needed to have both the astrometry, the motions of the stars on the sky, and the radial velocities together. So here's just another view of the same experiment. See, so the objective was to measure the gravitational redshift. This was the line of sight velocity we expected. And here's the deviations from a pure Keplerian orbit that we expected, about a 200 kilometer per second signal above what the Keplerian orbit suggests. Right, so this is what we expect to see. Ultimately, though, and now this measurement has actually been made in the past year, was to measure the periapse precession. So not only the redshift of the spectral features of the line, but also to watch the orbit not close. The orbit should precess as a prediction of general relativity. As it passes close by the black hole, it feels a slight bit of additional curvature of space-time, and the orbit will not close as a result. So I said future, but I'll show you that this has been recently measured. Now, this experiment and the entire galactic center experiment is simple in concept and difficult in technology. So the key ingredient for this successful 2018 experiment was precise and accurate spectroscopy and astrometry. You have to know that Keplerian orbit to remove it and see the relativistic signal on top of it. We had in 2018 now 22 years of astrometry, taking pictures of the galactic center, and 18 years of spectroscopy. And what makes it challenging is putting all of it together. So you have all of these images that you're taking, but somehow you have to get them onto a common ruler, common coordinate system. That may seem simple at first. The difficulty is that all the stars are moving. So if you have no stationary points, it's very difficult to establish a common coordinate system. Not to mention that the black hole itself is, while it may be at rest, is not easily visible every night. So we couldn't use the black hole to establish our coordinate system. In addition to getting everything onto a common and very precise coordinate system, there's also the problem of confusion and crowding. Even with our largest ground-based telescopes today, we still get confused and multiple stars overlap each other at times. This is an example of that confusion. This is a picture at the Galactic Center, and you can see the stars overlap, their tracks on the sky overlap, and they cross each other, and their astrometry is compromised as a result. And we have to disentangle this confusion in order to see the orbits properly. So despite all of these challenges, we made the measurements in 2019. Both groups were able to detect for the first time that relativistic redshift signal. And on the upper right, you see the orbital measurements that we now have full coverage. The star is actually wrapped around. We've seen its full orbital period and more. And on the lower left is the radial velocity signal, the line of sight velocity that was measured. The star at closest approach was moving up to 4,000 kilometers per second for this particular star, SO2. And on the lower right is the redshift signal removing the Keplerian orbit. You see a clear excess at closest approach of about 175 kilometers per second. The best fit model gives you a redshift parameter, a measure of how general relativistic you are, of slightly less than 1. 1 is what you would expect for GR. But within the uncertainties, it was completely consistent with GR, and subsequent measures since 2018 continues to show that GR seems to be alive and well and working just fine at the Galactic Center. So over these past 25 years of studying the Galactic Center, the team has grown tremendously, and we continue the experiment. As I said, there are many new questions that have opened up, and even the probes of the potential and general relativity continue. So our gravity probes are getting closer in and more precise. If you look on the right, this is a nice plot by Genzel and the gravity collaboration. Oops, pardon me. Yep, sorry about that. That shows you, one moment. There we go. That shows you how close we've gotten. Remember, we started out at 0.1 parsecs in the late 90s. And we've moved down to, for stars at least, all the way down to 0.001 parsecs now, 10 to the minus 3 parsecs. Or in gravitational radii, it's about 1,000, maybe a couple of thousand Schwarzschild radii away. There's also the gas that we're now studying as it accretes onto the black hole. That gets us in even closer. So the gas we think we are seeing is coming from a region that's just a few gravitational radii out, a few Schwarzschild radii. And then soon, we hope the Event Horizon Telescope will probe all the way in to measure the event horizon radius itself, using the silhouette techniques that we've already seen for another large black hole in a distant galaxy. The Event Horizon Telescope has many observations of our own center of our galaxy, but the picture is apparently more complicated than anticipated. And so they're still working on the reductions for that data set. We've moved beyond measuring the mass and density of the black hole, and we've moved into solidly with 2018 experiment, and now moving on, we've gone into the territory of testing general relativity formally. And on the left is a plot showing various parameters that you can test to test modified theories of gravity. Still to this date, general relativity, which you can see is this FSP = 1 line, is still the best solution for all of the observations that have been obtained at the Galactic Center. Other questions, I'll pose the next series of questions as things that we're trying to learn about the Galactic Center today. Does general relativity change around a supermassive black hole? That's still a question, an experiment we're doing. We've learned a lot about the stars around the black hole. So from an astrophysical standpoint, this nuclear star cluster is also a feature we see in almost all galaxies. The supermassive black hole is surrounded by a nuclear star cluster, and that there must be a link between the black hole and this cluster. We know that black holes on a global scale have connections and correlations with the whole galaxy properties. The bigger the galaxy, the bigger the black hole. But how does the black hole know what kind of galaxy it lives in? It may be through this bridge, this nuclear star cluster. So we're learning quite a bit about this nuclear star cluster and the black hole's environment. In particular, the old stars that we see don't follow the kind of radial profile that we expected. If you plug into a computer and you do just a pure gravity simulation with a supermassive black hole and a star cluster, you should expect the stars to peak up in a cusp around the black hole. And yet we don't see that at our own galactic center, at least not yet. But remember, we are limited today due to confusion still with our telescopes not being quite big enough. So we have underlying questions. Do the stars actually follow this cusp that has been theoretically predicted, but that we don't yet see? We've been using our spectra to study not just SO2's radial velocity, but the stars in the cluster as a whole and measure their metal content. And what's remarkable is that we've seen some of the highest and lowest metallicity stars in the Milky Way at the galactic center in the same volume. So we have many questions about the abundances or metal content in these stars and how they got there and how they connect with their dynamics. One remarkable thing spectroscopy has also showed us is this young stars that exist around the supermassive black hole. Today, we can take spectra of many stars at one time using what we call an integral field unit spectrograph, which means you take a picture and every pixel in the picture gives you the spectrum. And so we've used that to identify hundreds of very young stars, only a few million years old, that somehow formed around the black hole. And then we can measure their 3D dynamics. Their orbital periods are much longer, 1,000 years maybe. So we won't see the whole thing. The stars with orbits in the middle are in that innermost black dashed circle. These young stars, some of them are young, but these young stars continue out to much larger radii. And so these young stars have quite interesting dynamical structure and an unusual mass function, meaning their distribution of masses doesn't look like what our local solar neighborhood looks like. There's the orbiting stars in the middle, those S stars, the SO2 or S2 stars. Many of them are also young, and we don't understand how you can have star formation in the strong tidal fields and harsh environment around the supermassive black hole. In order for stars to form, you have to have a big gas cloud collapse into a star, and yet the tidal forces should rip apart any gas clouds that exist in here. So we have many questions about the young stars. How does star formation proceed around a supermassive black hole, in particular so close? And those closest in stars, as I said, some of them, like SO2, are young. And so we're left with many questions about these young stars too. How did they get there? Were they born in this recent starburst? Are they truly young? Or were they deposited there through some dynamical mechanism Maybe a binary came in and got disrupted by the black hole and left one star tightly bound and one star ejected out of the whole Milky Way as a hypervelocity star. And lastly, we keep discovering things we don't know how to explain. Most recently, in 2015, an object was discovered that was heading into the supermassive black hole that looked quite unusual. It was only seen as a dusty red source with hydrogen emission, and it was heading in. So it was thought at the time it was some kind of small gas cloud of just a few Earth masses that would go in and accrete onto the supermassive black hole. Strangely, though, as we watched it pass through in 2016 or so, it survived. This is a measure of its brightness over time. And you can see that that closest approach, nothing changed. It just continued to stay its similar brightness. So this looks like some kind of envelope, puffy envelope of gas around some kind of mass sink, a star of some kind that we don't understand at all. This is unlike almost anything we've seen in the universe. And so there are still fundamental questions. What are these G-like sources, these very red, dusty, extended things? And very recently in the 2018 experiment, all of this astrometry has also allowed us to start to find the first astrometric binary candidates at the galactic center. Here's one particular example. What's fascinating about this example is that if you believe this astrometric wobble that you see on the right, the enclosed mass for this object would be a few hundred solar masses, which we don't know of any stars that are that massive. And so could this be the first signs of stellar mass black holes, very massive ones, potentially the merger products of merged binary black holes that are orbiting around the supermassive black hole? We fully expect there to be a swarm of stellar mass black holes at the galactic center. The question is, can we see it? So over the past 20 years or so, 25 years now, we've been collecting observations of the galactic center and building up this picture that we see. So this is showing you all of the stars that we know about at the galactic center and their tracks. We've run the movie longer than we can actually observe, but you can see all the young stars are marked in blue. All the old stars that we know about are marked in orange, and the weird things that we don't understand what they are marked in pink. And we have the very good knowledge of the orbits close in. And as we back out, you can see many more stars whose orbits are less certain, the ones without yellow orbit rings. You can see the dynamical structure around the black hole is very complex and has a lot of substructure, this disk-like feature that you see. And all of this is providing us more and more information about the supermassive black hole, the gravity that it experiences and imposes, and how it connects with the surrounding nuclear star cluster. To continue to make progress in our studies of the galactic center, we do need to move to a bigger telescope. A larger aperture, a larger optic is essential to probe with greater detail those stars, beat confusion, and get closer into the black hole and improve our astrometric measurements and answer all of those questions that I just posed. And we're looking forward to the next generation, one of which is the 30-meter telescope. I'm going to show you here a picture of our current Keck adaptive optics system and the picture of the galactic center. This is that star SO2, and you'll see it orbit around. So this is real data based on the left. We're trying our best to upgrade our current telescopes with the best in the world adaptive optic systems, new adaptive optic systems that are even better. That's what will be shown in the middle. And on the right is a simulation, both of these are simulations of what we anticipate the 30-meter telescope seeing. So I'm going to play this movie and you will see that this improvement in resolution is essential to continue to make progress at the galactic center. So here's SO2 looping around. And here is that same star SO2 and all the stars we know about, plus many more stars we don't know about that we've simulated as planted them in there. You can see with the 30-meter telescope class of telescopes, we move from a domain where we have one or a few orbits we can study in detail to 100 orbits, 100 stars we can resolve and follow as they move around the black hole, using them all for probes of gravity and for understanding the supermassive black hole and its environment in more detail. So I will finish here with just one last little bit. I've been working more recently on searching for isolated stellar mass black holes. I don't want to spend a lot of time on this, but I thought we use the same exact techniques that we've developed on the Galactic Center over the past 25 years to now study these smaller black holes, the cousins that are located throughout the Milky Way. And for black holes in general, we see them through accretion processes. Now we can hear them from gravitational waves, but all of the stellar mass black holes that we know about so far are in binaries. This is the census, actually this is out of date. LIGO and Virgo have just released a new sample. The entire census of black holes as we know it, all of them are binary star systems. So that leaves us with many questions about the stellar mass black holes in our Milky Way, including what are their numbers, what is their mass distribution, how many are in binaries and how many will merge, do they get kicked during supernova, and do those primordial black holes, those very speculative ones, do they even exist? So I've been using the technique called gravitational lensing, using the gravity of the star and how it warps the light around it to search for black holes. This is a technique you can get familiar with by looking at a light source through a wine glass. It acts as a lens, the bottom of the wine glass. You can see the lens can make rings, as you see on the lower left, or separate and make your light source look like multiple images, two or three images, as you see on the right. This is exactly the technique that we're using to find stellar mass black holes. Black holes, if they pass in front of a star, will make multiple images. And these multiple images, this gravitational lensing effect, can be seen and used to measure the mass of the lens and prove that it's massive and not luminous. Again, that's what we need to prove the existence of a black hole. Unfortunately, in our own Milky Way, we can't resolve those images. We can't separate them with our telescopes, either this current generation or future generations. So we call this microlensing when we cannot resolve them. There is still a signal that we can see. So here's a cartoon showing what this process looks like. This would be the black hole. In red would be a background star, and it would produce these two multiple images, which we can't resolve. But if we look at the light of the star and watch it go with time, you can see as it passes by, it will magnify, just as we saw with the wine glass, and the star will temporarily look brighter. This is the signal of gravitational lensing. It's one of the signals. Unfortunately, this brightening alone is not enough to weigh and measure the mass of this lens. So the photometry or brightening is insufficient. We also need to measure the position of the star. There's an astrometric effect. Same thing, here's the lens in blue and a star passing by in green. And it looks, because of these two images that get created in yellow, if you add the flux weighted light together, the position of the star seems like it moves with time, which is shown in red, right? And so instead of the star moving in a straight line or wobbling due to parallax, it will have a perturbation that you will see on the sky. And the size of this offset is proportional to the square root of the mass of the lens. So this astrometry, just as measuring the stars orbiting the supermassive black hole, we use the same exact techniques. In principle, can show us the mass of the lens and allow us to prove whether it's a black hole. Yeah, sorry about that. Let me pass on through these. So this is an experiment that we're just starting. The measurements we're taking, they take a long time to measure, just as with the Galactic Center. Apologies here. And the astrometric signal that we expect to see is about at the limits of our technological capability. It's about 1 milliarc second, and our current measurement precision is about 0.1 milliarc seconds. So in principle, we can conduct this experiment, and we are attempting this experiment now, but certainly with the next generation of telescopes like the 30-meter telescope, finding isolated black holes, free-floating black holes, should be routine. And so we've started this experiment. We're finding these events, and this is a simulation now. We expect to see the black holes with big astrometric signals just in the coming years. We should be able to detect them for the first time and start to build up a census and compare it to our predictions for where and how many black holes there are in the Milky Way. So I think the study of black holes in the Milky Way is really ramping up. We've found the big one in our galaxy, but we're on the hunt for many of the small stellar mass black holes still within our own galaxy. And we're still studying the properties of the supermassive black hole at our own galactic center and its surrounding nuclear star cluster. So it's a rich time to be studying black holes. And I think that will continue, and hopefully we can come back and talk again later and tell you more about new black holes that we're finding all the time. Thank you, and I'm happy to take questions.
Thank you, Jessica, for your wonderful and very complete talk. It's time to questions. Anyone have a question? Remember, you can write your question in the chat. Okay, we have 2 questions there from Milo Vitrago. In the multi-messenger astronomy frame we live today, how are the observations and open questions you showed us will benefit from combining that data from LIGO and the Event Horizon telescopes?
Yeah, so for the galactic center, the LIGO sources, the gravitational wave merging black holes that we're finding, it's not at all clear how they're formed, where they come from. And one of the running theories is that centers of galaxies are dynamical engines that can produce these binary black holes that will then later merge. Now, there are competing theories, but if we could find the stellar mass black holes around the galactic center, that would go a long way to understanding whether black hole binary formation at galactic centers is an important mechanism. So that's definitely one connection that we need to make. With the Event Horizon telescope, it's probing the innermost accretion flow, and they absolutely need all of the information that we provide about the orbit and the gas and the integrated accretion at the infrared wavelengths. So those, we are very tightly tied with the Event Horizon telescope. Lastly, for high energy, there's a lot of X-ray, interesting X-ray phenomena at the galactic center. And we are trying to connect with that, trying to understand where the X-rays and even gamma ray signals at the galactic center and around the galactic center, bubbles we think that are blown out of the galactic center, where they come from. That connection's harder because the spatial resolutions are so different, but there's a lot of studies of the prior history of the black hole. Did it previously launch jets in an earlier lifetime?
Thank you, Jessica. There is another question from David Vanegas. Is there any effect of dark matter on the measurements done at the galactic center? If so, that is a study of SMBH carried out for decades. Something about dark matter?
Yeah, so the orbit of the star SO2 going around the black hole, I said it precesses due to general relativity. So it turns out that dark matter, or any kind of cusp of matter centered on the black hole that's slightly extended, will precess the orbit in the reverse direction. This is the experiment that we're trying to do right now, which is to measure that precession forward or backwards, and both constrain general relativity and constrain that cusp of dark objects. Now, I say dark objects because at the moment, we can't quite detect that it's there. We can put limits on it, but we don't know whether it's there. And we haven't, as a result, we don't know whether it's dark matter or a swarm of black holes or a swarm of neutron stars or something else entirely. So I think long term, we absolutely hope to measure that cusp of dark material and determine whether it's potentially dark matter or a swarm of black holes, for instance, dark objects around the supermassive black hole. As so far, though, we can only put limits. We can't actually detect what that mass absolutely is, but we're right on the cusp of being able to do that.
There is another question from Jairo Alexis about the primordial black holes. What is the origin of those black holes and why are they necessary?
Yeah, so the origin during inflationary periods in the universe, you have a density of, a spectrum of densities within the universe. And so at the far tail, there are some predictions that that spectrum continues on to the point where you have small regions that have very high density, high enough to collapse and form a black hole. It's very speculative whether that actually existed, that spectrum extended to that high of a density. But it's an attractive option for explaining dark matter. So we don't know what dark matter is, if it's a particle or a fundamental particle of very low mass or something else entirely. It used to be that that theories abounded that dark matter was made entirely of free floating black holes, that it was all just black holes. And there were some experiments that ruled that out, but it turned out they only ruled out masses that were very small, much smaller than an Earth mass, for instance, for the black holes making up dark matter. Those experiments were things like Macho and Eros, using gravitational lensing, actually. So with the discovery of massive black holes from LIGO, these 85 solar mass black holes, which are actually more massive than we think stars can produce themselves, it's been revived that perhaps dark matter could be made up in part or in whole by black holes that are 100 solar masses or 200 solar masses or 80 solar masses, for instance, and that these would be primordial black holes. So although it's a speculative theory, there's still a lot of interest, given that dark matter particles still haven't been found, as to whether dark matter could be made up of these primordial black holes. And the gravitational lensing experiments I talked about at the end are sensitive to those primordial black holes if they exist.
Okay. There is a final question from Diego Restrepo. What is the current status of the catalog of black holes in our galaxy? What are the expectations regarding the abundance and distribution?
Yeah, so in our own galaxy, we expect from theory there to be about 100 million to maybe upwards of 1 billion, but that number alone is uncertain by an order of magnitude. The number in our galaxy that we've discovered is less than 24, right? So of all those billion black holes, we know about 25 or so, 23 in fact, and all of those are in binaries accreting from a companion. The black hole masses that have been measured are sort of in the 5 to 10 solar mass regime within our Milky Way. And it's quite a different distribution than the kinds of black holes that LIGO is finding. So we're nowhere close to having a complete picture of the black holes. We expect many, hundreds of millions more to be free floating and out there available for discovery with microlensing. But we have yet to confirm a black hole with microlensing firmly. Like I said, we're right at the technological edge, and it's a long time scale experiment. So we have some good candidates we're working on, and we hope to publish in the next couple of years.
Okay, so thank you, Jessica, for your time, for your very complete discussion session, and for your talk, very illustrative talk. So this is the final of this first part. We will make a break for around 10 minutes. So we will meet again around 11:15. So thank you very much.
Thank you for having me.
Thank you. Thank you, Jessica.
Okay, so I think we can start again now. The next talk will be from David Bernstein. David is Colombian. He's a Colombian physicist. He currently works at the University of California, Santa Barbara. He got his PhD from the University of Texas, and his main research work is string theory and quantum field theory. He will tell us about gauge theories on quantum computers. So, David, you may start when you want. Thank you.
Thank you. Can you see my screen?
Yeah.
Okay, very good. Okay. So, thank you for the invitation. I'm going to tell you a little bit about recent progress that has been happening on trying to implement interesting computer codes for physics in these new devices that are coming up online that are the quantum computers. And because I do gauge theory, I'm going to talk about gauge theory on quantum computers. But it is being applied in much more general setups right now. So let me remind you a few things. First, we all love the standard model of particle physics, which is our best theory of nature and has been verified in countless experiments, is based on the principle of gauge theories. So this is the standard world that we know from CERN. Basically, we have the standard model fermions, the quarks, up, down, charm, strange, top and bottom, and the leptons, the electron, the neutrinos, and their heavier cousins, the mu and tau. And then there's what we call the forces. And the forces of the standard model are comprised of the electroweak theory, the photon, WZ bosons, and the thing that I want to concentrate on most right now, the gluons themselves. And the reason to focus on the gluons is that they're strongly coupled. They require going beyond perturbation theory. So the usual techniques of Feynman diagrams will not work for understanding QCD. So how does the proton kind of bind together and get its mass? And what happens when you scatter of a proton? And these events of scattering require strong coupling physics. There's a lot of other setups where there's strongly coupled phenomena, like strongly coupled electrons in materials, where the interactions between the electrons are so strong that the idea of perturbation theory breaks down. And what we would want to do instead is have a simulation of what's going on to, in some sense, get around the problem of strong coupling by a computation. Here's what's important. For many interesting phenomena, we also require real-time physics. For example, if you have a system and you perturb it and you want to see how the system dissipates, that requires following the system in real time. And we want to do that in very quantum systems. So what we would like to do is basically solve the multi-particle Schrodinger equation and calculate what happens. But there's usually something called the sign problem. And this is basically that if you have, let's say, a path integral representation of the evolution in time of the Schrodinger equation, you have to sum over all paths. For each path, you take the exponential of I times the action. And this factor of I basically means that you have a phase. And when you have numbers with phases, there can be destructive interference. And this actually happens all the time. And when you have destructive interference, you get cancellations. And what that means is that the most efficient method that we know to do computations in quantum systems breaks down. Monte Carlo methods usually require that when we do a computation, that we have a probability distribution, so that when we take averages, after we've generated the probability distribution, we are in good shape. And usually that involves exponential to minus the action, and the action needs to be real. In this case, with exponential times the action, Monte Carlo just doesn't work. You're summing pluses and minuses, and they cancel, and it's not even clear that you're in the right regime in field space to describe the phenomenon. So the idea is that there are these types of problems, and we would really like to understand how to solve these dynamical problems. And perturbation theory is not working, and Monte Carlo is not working. So what else could we do? Well, we could try solving the Schrodinger equation for many degrees of freedom. But if for each degree of freedom, the dimension of the Hilbert space is A, which is usually bigger than 1, then the dimension of the total Hilbert space is this number A to a number of degrees of freedom. And then when we want to do physics in the thermodynamic limit or the continuum limit, we want to take the number of degrees of freedom to infinity. So the dimension of the Hilbert space grows exponentially in the number of degrees of freedom that we want to keep. And this is one of the main reasons why solving problems directly in quantum mechanics is hard. Let's say you have one particle, you have 10 states, you can still do it. 2 particles, it's 100, that's okay. Once you go to 1,000 particles, we're talking about 10 to the 1,000, and that's more than the entropy of the whole universe. So no computer will be able to deal with that. So in computational language, what we need is an exponentially large number of resources, and then standard computational methods will really not work for these systems. So again, this is just a statement about problems we would like to solve, and what are the barriers to solving them. And this is where new advances in technology are making possible changes in how we actually go after simulations. So the idea is that if we had an ideal quantum computer, then what a quantum computer is actually a Hilbert space. It's a quantum system. So the memory is a Hilbert space itself. In a certain sense, what that means is that the interference phenomena is built in the memory. The Hilbert space of a quantum system grows exponentially in the number of qubits or little pieces that you have to control. So the problem of the exponential growth of resources is automatically taken care of by the type of device that we're working with. And the other thing that's special about this Hilbert space is that we can, in principle, do the Hamiltonian evolution directly. So what we would do is set up the Hamiltonian and on this system, and then evolve in time directly in the system and then measure. And there's always the problem that even after you've done all that, you still need to find the correct initial condition, but that's a problem for another day. My talk today is really about how do we do the evolution in the systems, and what does it take to make it happen. So let me tell you what the state of the art in these quantum computers is right now. There are quantum devices out there, and they're starting to become available. And then there's this quantum computer for IBM that has about 50 qubits, which is starting to come online. There's a device of Rigetti with about 20 qubits. There's the quantum computer of Google, which had like 42 or 50 qubits also. This grew off an offshoot of some research that was being done in Santa Barbara. There's also other technologies which are based on ion traps. And then there's a lot of systems where quantum control has evolved to the point where we can have many qubits and have them interact, and at least in principle, set up some evolution with some special type of initial conditions and see what happens. Okay. So the idea is that these devices are there. They're not perfect. They're actually quite far from perfect yet. But it's starting to get to the point where we can do something and we can try to understand how much effort will it really take to do the calculations that we need. So how many qubits? Well, at the moment, at most of order 50. So the idea is that right now we will not have a quantum computer that will solve the problems of gauge theory that we care about. QCD is still very far beyond what we can solve, but with 50 qubits, the dimension of the Hilbert space that you have is already 2 to the 50, which is about 10 to the 15. To give you an idea, this is 1,000 gigabytes. This is more than most computers' memories, although there's some big supercomputers that can deal with this. But you don't just need the Hilbert space. This will be kind of the state of the system. You still need to program the Hamiltonian. The Hamiltonian will be a 10 to the 15 times 10 to the 15 matrix. So the total memory cost, if you had some random Hamiltonian, would be in memory about 10 to the 30 or 10 to the 45. And that is still beyond any computer on Earth. So the idea is that this is a big Hilbert space size. And it's kind of beyond what regular computers can do. This is why when the big paper of Google came out about quantum supremacy, it was exactly about this, that the scale was too large to be simulated by a classical computer. Okay, so here we are, we have this Hilbert space size, and then the big question in this type of devices is, what does it take to implement the gauge theory on such a device? Okay, so all of this was the introduction, and now really going to tell you what the rest of the talk is about, is about what are the ideas on how to put a gauge theory on one of these devices. So the first thing is we need a Hamiltonian formulation of gauge theory that can live on a lattice. So we need a special formulation of gauge theory, which is not the Euclidean lattice gauge theory, but it is a Hamiltonian formulation that we can actually implement on a quantum memory. Then I'll tell you a little bit about, once you have this formulation, what type of truncations do you need to do and approximations to actually reduce the problem to something that can be implemented on a finite number of degrees of freedom on a finite quantum memory. And then there's actually many choices here. The choices will become apparent later. But the idea is that this actually needs to be done. This is something that cannot be avoided. I'll show you just one of the choices. And I'll go with a simple example, which is U1 gauge theory in 2+1 dimensions. Again, dimensionality here plays a role. 2+1 is kind of the smallest dimension, which is interesting. In 1+1 dimensions, gauge theory is a little bit too trivial. In 3+1, you need too much memory. So 2+1 is kind of a middle ground. Then I'll tell you a little bit about how you build large representations of this U1 dynamically. And then I'll talk a little bit about how the gauge theory implementation would look like in practice. Okay, so there's a standard Hamiltonian formulation of lattice gauge theory. It's called the Kogut-Susskind formulation. The idea is you have a lattice, and in between the lattice sites, you have links, to which link you associate a unitary operator or a unitary variable. The idea is that this is the classical position space variables of the lattice gauge theory formulation. So you have these U's, and you choose the gauge condition where A0 is equal to 0. This is part of the formulation. But the idea is that the classical variables are these unitary U's, they're group elements on the links, and their canonical conjugates, which are some velocity fields. And the canonical conjugate to the U variables are the electric fields. The best way to represent them is by taking the time derivative of U and multiplying by U inverse. And then when you do this electric field is actually valued in the Lie algebra of the group. And that brings in a lot of powerful tools of representation theory. Okay, so the U variables themselves are parallel transports. You basically integrate from x to y exponential to the I a dx. If the system is non-abelian, you need to do this with a path ordering. So you need to actually be careful about what the U really is. But the idea is that essentially U is like the exponential of the spatial component of A. And then when you have these U, they transform under gauge transformations as follows. So you multiply by group elements on the left at position Y, and you multiply by the group elements inverted on the right at the position X. So if Y and X are the two lattice sites that the U variable is linking, then you have gauge transformations at the lattice sites indicated by Y and by X, and then the links transform under both gauge transformations. Let me point out something over here. Here I use the electric field as U dot U inverse. When you do a gauge transformation, which is constant in time, it goes past the U, and then the one that's acting on the right cancels between the U and the U inverse. And then you just get the one on the left acting on the left, and the one on the left inverted acting also on the right. So if I write it this way, this electric field is adjoint valued with respect to the left gauge transformations. If I use an electric field which is U inverse U dot, then it does so under the right gauge transformations. So the idea is that you have two choices for the electric field. They're equivalent. One of them transforms on the adjoint of Y, and the other one under the adjoint of X. But they are related to each other in a simple way. Okay, so this is the set of dynamical variables. And then there's something called the plaquette. A plaquette is a gauge invariant operator. If you start at 1 and then go to 2, and then 2 to 3, and 3 to 4, and 4 to 1, then you can have U12 times U23 times U34 times U41 and take the trace. And you can show that this object over here is gauge invariant. And these plaquette operators are basically small Wilson loops on each one of the lattice faces. And when Wilson did plaquettes for setting up gauge theory on Euclidean lattices, the plaquettes are standard objects, and they roughly behave like the magnetic field squared for the phase 1, 2, 3, 4 that I have here. Okay, so now that you have these, this is the classical Hamiltonian. You have an electric field coupling constant, GE. You sum over the links, the electric field squared. You need to take a trace here to make sure that it is gauge invariant. So the Hamiltonian is gauge invariant for the electric part. The electric field squared shows up, and then you sum also over plaquettes, and you sum over all plaquettes. And then that gives you the magnetic field squared. The electric fields, because they are in the adjoint, end up acting under Poisson brackets as generators of the local gauge transformations for the gauge link, and they act as the Lie algebra itself. So when you take the classical Hamiltonian and you quantize, the electric field variables can be replaced by the Lie algebra generators of the gauge transformations, and then they will act on the unitaries and the plaquettes. Okay. Now the problem is that once we've decided that this is what we want to quantize, we need to take this problem and write this Hamiltonian in a memory that is made of qubits with very few interactions per qubit. This is important as a practical matter. And then I remind you that what a qubit is a two-level state system. Basically, it's a spin 1/2 register, but there's no Fermi statistics between them. So the two-level state systems are independent. So what we need to do is take the Hamiltonian that we have there, which is still abstract, and we need to understand how this actually looks in a physical basis so we can actually implement the Hamiltonian with the qubits themselves. So I told you that the variables U are position representation like objects. So U's are position, the electric fields, the U dots are their canonical conjugates. So if I make a wave function out of U, what I should get is some element of the L2 functions on the classical variable U. The variable U is continuous, so the L2 functions on U are an infinite dimensional Hilbert space. So the first thing that happens is that even after we've truncated to a lattice, we're not done, because the local Hilbert space at each link is still infinite dimensional. In a certain sense, this is the statement that the U's are bosons, and with bosons, there's no Fermi statistics preventing you from just piling more and more information on one side. So what we need to do is we need to take this infinite dimensional Hilbert space and make it finite somehow. So there's a lot of ways to do it. One way which people tried, which doesn't work well, is to discretize the U variable as a group. This turns out to only work for U1. The reason is that the other non-abelian gauge groups that we could have do not have discrete subgroups that can become dense. So for U1, you can take Zn, and then when you take n to infinity inside U1, you get something that is dense in U1. That's not true for other non-abelian groups that are available. So you can't really extrapolate to a continuum in these other setups. The other idea is that instead of discretizing the classical variable U, you can try to discretize the space of wave functions directly. And then if you do it well, you keep gauge invariance. And this approach has a lot of history. Here I'm giving just a list of papers that are relatively recent, but people have been trying these for a lot longer. Okay, but mostly all the ideas end up with the same mathematical physics that I'm going to describe over here. Basically, the first thing you do is you decompose the space of wave functions that you can have, these L2 functions on U, into representations of the gauge transformations. Now, if you remember, on U, there were gauge transformations acting on the left and on the right. So when you decompose into representations, you need to do so both with respect to left multiplication and right multiplication. So there's actually a very important piece of mathematical physics that tells you what this decomposition is. It's something called the Peter-Weyl theorem. It says that the L2 functions on U are a sum over all unitary representations of the group U of our representation R tensor, the conjugate representation, and the left R is for the left action of the Lie algebra, and the R bar is for the right action of the Lie algebra. So the idea is that when you look at this, you get a sum over R, and the variable R is discrete. So at least now this L2 of U is a countable Hilbert space with a countable basis, which is counted by this R, rather than an abstract L2 of U, where we started with wave functions that depended on the continuous variable U, which was an uncountable basis if you think of the U as a classical variable or as the position X. So here we are, we have this decomposition. And then the idea is that when you look at this decomposition, the kinetic terms, the electric terms, is actually the quadratic Casimir of this R or of this R bar. They have the same Casimir. Basically, we keep the electric fields or the Lie algebra action, and we modify the magnetic variables. So when you do this truncation, this is a representation in terms of an electric basis for the wave functions rather than a magnetic representation. The advantage of this truncation, or of just writing it this way, is that you have a full list of gauge transformations that you can preserve, and you preserve them if you preserve complete representations of the Lie algebra. So the other thing that happens is that because the electric field, the kinetic term, is the quadratic Casimir, the higher representations cost more energy. So if you truncate in the Casimir, you can truncate to low energy effective field theory, at least as far as the electric field is concerned, if you put a cutoff in the Casimir. So the idea is that you have this Hilbert space, more Casimir or a bigger Casimir costs more energy. So if you want to do a low energy truncation, a sure bet or a bet on how to do that effectively, at least locally, is to go to some truncation in the Casimir of the group. Okay. So the goal is now write this truncated theory with some cutoff on the Casimir in terms of qubits. So we need to encode the link space into qubit. There are many choices. Write the Hamiltonian in terms of qubits, and then finish that. And then it turns out that this can be done for arbitrary gauge groups. It's more complicated. It's something based on something called D theory, which was developed by Richard Brouwer, Uwe Wiese, and Chandrasekaran. The main idea was that these U variables are composite. We have not costed the resources for this yet. And then there's an extra step, which is even once you have these, the quantum computers cannot generate arbitrary Hamiltonians. They can generate something slightly different. So to do the time evolution, we need something called the Trotter representation, or the Trotter steps. So let me tell you what that is. The idea is that if you have a Hamiltonian, and if the Hamiltonian can be written as a sum of various Hamiltonians which involve few degrees of freedom, then the exponential of the Hamiltonian times time can be approximated by products of exponentials of these smaller unitaries with the HIs, which involve few degrees of freedom at a time. And then the Trotter theorem is that when you take the limit when n goes to infinity of the right-hand side, you recover the left-hand side. And the reason why it works is that in these exponentials, the commutator of two of these pieces, you use the Baker-Campbell-Hausdorff formula. It goes like 1 over n squared. And then this 1 over n squared is important because you only have a power of n outside. So basically the commutators can be taken to go to 0 as n goes to infinity. And that means that the order inside the expression doesn't matter too much. So this individual T hi over n pieces, in principle, can be computed in a finite number of steps, many of them in parallel, and then we need to assemble the product. The big bottleneck for this stuff is that quantum computers are not perfect. So you can only do so many operations on each qubit before you lose coherence. So what that is called in quantum language is what's the depth of the circuit that you can run? How many operations can you do on a single qubit before you lose the information? So we need to do the right-hand side in such a way that we have as few gates as possible so that the clock doesn't run for too long. And then the total simulation time is the number of trotter steps that we can make times the time parameter per step. So it's n, little n times t over n. So if we can control t over n and we can do it n times, then we can evolve the system. Let me tell you that for the time being, the results are somewhat disappointing. We can do one trotter step. So that's not enough time to do anything very useful. But the idea is that if we can do one trotter step now, in a couple years, when the computers get better and when the coherence time improves and when the fidelity of the gates improves, we will be able to do 10 or 20 trotter steps. Once you're talking about 10 or 20 trotter steps, that's enough time for information to spread around and to start getting interesting physics. So the idea is that we're not that far from where we could be, and we're getting to a point where this is starting to become feasible. Okay, so what is the idea of a trotter step or of a quantum computer? You're always running against the clock. I like to cook, so my favorite way to think about this is that you buy fish in the market, and if you don't have a refrigerator, you need to cook it quickly, otherwise it will spoil before you get to eat it. So when you're thinking about quantum computing, you really need to think about how fast can you get the fish to the table with the fish not spoiling. And what that means is that because you're in a hurry, you have to make a lot of compromises. Eventually, when the computers get better, we can take our time, but for the time being, what we need to do is really see how far we can push it before the system breaks down, which is relatively quickly. Okay, so now here's a compromise. What is the gauge theory that we are costing and trying to simulate and trying to understand? Is just U1 gauge theory in 2+1 dimensions. This is joint work with Richard Brower at Boston University and his students, Valier, Howard, and Kawai. And then because we're doing U1, let me start with something simple, which is what's the space of L2 functions on a circle? It's a sum over charges of the representation of the charge tensor, the representation with minus the charge. This is the right-hand side is the Peter-Weyl theorem. So you decompose the wave functions on the circle by their charge. There's a charge for acting on the left and a charge for acting on the right. They're the opposite of each other. And then it turns out that this is just the Fourier decomposition of the circle. So the variable u that we like is just exponential to the I theta. It's a unitary of 1 by 1. Theta is the classical variable on a circle. And then the electric field is the conjugate variable of theta, and it's minus I dt theta. So the naive truncation that you do is you take a cutoff in the charge symmetrically. So you do L2 of S1, and you say, instead of doing this sum from minus infinity to infinity, you basically take the Hilbert space, which is the sum of exponential to the IQ theta, the low Fourier modes, where Q has been bounded above by some maximal charge. Okay. How does Q, U, and U star act? Q needs to measure the charge. So Q on a state of charge Q measures Q. That doesn't change. U on Q, if U has charge 1, then Q acting on the left-hand side of this needs to be something of charge Q plus 1. So there needs to be a number alpha Q that tells you how U is acting on the state of charge Q. And U star acts by the conjugate. It's the adjoint of U. In the continuum limit, meaning without the truncation, all the alphas should be equal to each other and to 1. But the idea is that in the low energy effective theory, the Q's get truncated and the alphas don't need to be all equal to each other. So if we just aim to preserve gauge transformations, all we need is that the commutator of Q with U is equal to U. So the alphas can be somewhat arbitrary. So the next question is, what is the plaquette? On a single link, you'll have a U and a U dagger, and then there will be other U's nearby, but on that link, it'll look like beta U plus beta U dagger. So on this single link, how will it look like? The Hamiltonian of the one link will have something that grows like the charge squared on the diagonal, and there will be something which is just on the nearest of diagonal with these values alpha q. And the important thing is that alpha q is bounded both in the continuum limit where you take the full U1 and also in the truncated theory. So these alpha q's are of order 1, and it depends on the electric field coupling and the magnetic field coupling, how strong these off-diagonal pieces are. But the idea is that the diagonal pieces are growing like q squared, and the off-diagonal pieces stay finite. So if you're doing perturbation theory relative to the electric field, these off-diagonal pieces will contribute terms that are subleading because the energy denominators are growing with q. So q plus 1 squared minus q squared, which is what would appear on the energy denominator, is getting small. So the idea is that once you think of this on the link, you see that approximating by the truncation is actually still good because the things that you're throwing away will give small perturbations to what you're trying to compute, so long as the beta alpha q are small relative to the value of the charge. In practical terms, the way to do this is to make beta small, but that's kind of the wrong limit. Usual continuum limit, we need to take the magnetic field stronger than the electric field, but we cannot do that just yet. In any case, here is how the system looks like, and we see that the truncation makes sense from the point of view of effective field theory in the Hamiltonian setup. So now we need to do this on a system built with qubits. You're starting to see that things are more and more explicit as we get along. So I'm going to make a choice. This is a choice that I can make where I take Q to be the generator of angular momentum in the z direction, and U and U star to be L plus and L minus generators of angular momentum divided by some maximum L of representation theory. Okay. So if you use angular momentum, then what you find is that these alpha values are L inverse square root of L times L plus 1 minus M times M plus 1, where M is the principal quantum number, or the LZ quantum number of the state that you have. And then when M is small, this difference is quadratic in M, so that's small relative to the L times L plus 1. So the alphas are approximately constant. So at low values of M, meaning M of order 0, and large L, this is good because these are approximately constant to quadratic order in M. Okay? So the alpha M's are of order 1 plus some correction that goes like M squared over L squared. So the corrections are small. So here's another fact. For any system of qubits, any Hamiltonian can be decomposed in terms of products of polymatrices. So your Hamiltonian can be written as a constant plus a linear combination of the individual polymatrices plus sums of tensor products of polymatrices of the different qubits, plus so on and so on. And the more polymatrices a term has, the harder it is to simulate in quantum computers. And one way you should think about quantum computers is that they can do 2 qubits at a time, more or less okay. This is the type of control that we have nowadays. And then anything else that has more than 2 qubits at a time, you need to build by acting on 2 qubits in various orders until you get the desired term. So if you want to port to qubits, I'm going to make another choice here. I'm going to say that since each qubit has an SU2 of angular momentum, I'm just going to generate my total angular momentum by addition of angular momentum. So if I take the algebra theory, if I do addition of angular momentum, I still get objects that have the correct commutation relations for angular momentum. And now you see that my generators are sums of individual Pauli terms for each one of the qubits. And then because they are individual Pauli terms, they are accessible to someone who would operate the quantum computer. So by doing this, we're wasting a lot of states in order to get few interactions so that the angular momentum matrices are simple. So we need to make sure that the extra states that we are adding, because I'm using addition of angular momentum, this is not a space of dimension L, the maximum angular momentum that I need, but it's a space of size order 2 to the L roughly. So there's a lot of states on the right-hand side or in terms of these qubits that show up, and I need to make sure that when they show up that they don't spoil the calculation. When I do U squared, I get products of two L's. It has up to 2 Pauli matrices because L has single Pauli matrices. And if I do U, I have up to 3 Pauli matrices. And if I do U to the 4th, I have up to 4 Pauli matrices of different qubits. So if I have a plaquette with k sides or links, and each link has L qubits, and I just count how many terms I have, I get 2L to the k terms in the number of pieces of the Hamiltonian, and this is still too large. Basically, all the qubits in one angular momentum need to talk to all the qubits in the other angular momentum. So the problem is that this is all to all. You're having too many qubits talk to each other. So you run out of time before a single structure step works on current devices because you still need to spend the time to compute all the 2 to 2 qubits that you need, and there's too many of those. So the way to optimize this is to go to the smallest value of k that works. So plaquettes have to be at least triangles, so the smaller number is 3. And then the other way to reduce terms is to go to small l. And then we want to have L equal to 1 or 2 or some number like that, and hope that that's good enough. So what's the next idea? The next idea is the addition of angular momentum to get large spin. Hopefully works dynamically. So instead of doing all to all, hopefully you can set up some sort of dynamical interaction that tries to align the spins. So if you have a single link and you think of it as a single spin and you think of it as a ferromagnet, and if you add ferromagnetic interactions between nearest neighbors, then you can try to align the spins. So you can basically force the highest spin in the low energy dynamics. So if you try to do this and you want to preserve the U1, you need to take sigma x cross sigma x and sigma y cross sigma y. But the difference now is that instead of doing all to all in a single link, you're only doing nearest neighbors. So what you've done is you've split the link variable that we wanted and turned it into a one-dimensional ferromagnet. So you're kind of opening up an extra dimension where you're doing these interactions. And then you can do an interaction for the XX plus YY and a different one for the ZZ. It turns out we need different coefficients, the alpha and the beta. So in some sense, this is similar to the approach of the theory of Brouwer, Visi, and Chandrasekaran. They had not only a composite U, but they also stacked it in an extra dimension and hoped that coherence would make the system behave well and basically give rise to something that behaves like a continuous U variable rather than a bifermion composite. So in this other representation, the sigmas will be composite of 2 qubits. It will cost a few more qubits, but the idea would be very similar. And then the advantage is that with this composite representation, you can actually deal with UN rather than just U1 more generally. And we are working on that with Richard and with his group. We have ways to understand how to do this for higher UN, but I just want to talk about U1 today. So if you have an extra dimension, and you have the U and the V, and this is what they had, and you have trivial vertical links, then the plaquette will look like trace of U V inverse plus the complex conjugate. And then the U and V were replaced by polymatrices. So if you have the U and V replaced by polymatrices, what you get is something that has the right structure to have 2 polymatrices. And then it ends up in the same type of idea as before, some type of ferromagnetic interaction. So just like we did for aligning the qubits, we can also think of the plaquettes as living in the extra dimension. So there's an observation that a plaquette in the extra dimension is like an XX interaction that tries to align spins. So if you start with XXX, which aligns the spins, and add a ZZ interaction, you also get a XXZ spin change. So you get the same type of interactions before. The XXX is SU2 invariant. The XXZ breaks SU2 to U1. So you can think of these qubits as being ordered in the extra dimensions, and then you only have interactions between nearest neighbors. So instead of having all the qubits talk to each other, you're now only having very few qubits talk to each other. And when you do that, you are in business, because now you can, in some sense, hope to be able to run the code. If you do this right, the low energy physics will project on states with maximal spin, so long as you do the interactions correctly. When beta is different than alpha, this actually implements the electric field splitting in the multiplet of interest. So if alpha is close to beta, but there's a small difference, you get something that the splitting of the representation that we want ends up being split like the electric field squared, just like we would require for the Kogut-Susskind Hamiltonian. So the idea is that if you start with the XXX Hamiltonian, you preserve the SU2 on the ground state, the SU2 of the spin, but we need to break it to U1 by the electric field squared. The electric field squared is a sum over all Z's, sigmas, but you just do it over nearest neighbors. You're doing fine because of the Wigner-Eckert theorem. Basically, sigma squared summed over all spins, this one, and the sum of sigma I Z, sigma I plus 1Z are in the same representation of SU2. And then it turns out that you only have one coefficient to tune, and therefore they both act the same way on the states of interest. To apply, we need to make sure that we stay in the subspace of interest, which is the highest weight or the highest spin representation. But breaking this degeneracy needs to be kind of a lot less energy than bridging the gap to the states that are not in the maximal representation of SU2. And in the ferromagnetic language, that will be basically exciting magnons. So we need to make sure that we are not exciting non-trivial magnons. Okay, so we do the same with the plaquettes. We also split them in the extra dimension. If you did this carefully, it turns out that you still preserve the gauge invariant if you break it vertically. There's few operations per qubit. And then you preserve the gauge invariance, but you're still paying the cost that there's these extra states that are above the gap that you need to be careful about. So to implement the plaquette, you also require tuning coefficients, and you need to be careful not to get out of the Hilbert space where you need to be. There's a problem, or there are issues in that the plaquettes involve 3 qubits, and I'm only allowing you to have operations between 2 qubits. So I need to explain some of that. So in low energy physics, one can recover the Kogut-Susskind Hamiltonian with few operations per qubit. The issues that we get are what happens when we tune the coefficients and the Trotter time. We're still working on that. So what we do is brute force. So we do 2 qubits per link. So the physical Hilbert space is of dimension 3, the SU2 triplet, plus a singlet, because you have 2 qubits, that's 4 states. And the singlet should be the UV physics magnons that you don't want to show up. So in total, if you have a triangle plaquette and each link has 2 qubits, you need 6 qubits per plaquette. And at least 1 plaquette can be simulated, maybe 4. So how does a plaquette look like? Here's a link. The link would be 2 qubits. You can do the 2 qubit operations that you want, and then you can align the qubits to have the triangle plaquette as follows. I'm going to assume things about the architecture. They're good assumptions in that some of them seem to behave this way. The qubits are on a lattice, and I can do arbitrary nearest neighbors. And then the assumption is I can perform arbitrary 2 qubit operations between nearest neighbors. If you actually look at what these computers can do, it's not quite true that you can do arbitrary 2 qubit operations at each step, but you can do certain 2 qubit operations that let you, after enough steps, generate arbitrary 2 qubit operations for each one of the pairs of qubits. The vertical Trotter step is easy. That's the one that generates the electric field squared. It's the horizontal Trotter, the one that corresponds to plaquette, that we need to implement and understand how it works. So this is where we take all these L pluses and L minuses, and we try to understand how that plaquette looks like. And you decompose everything in terms of polymatrices. So you have 3 polymatrices, and then you can check what these triangles do. And what you get is that the unitary that you need to implement is this product of 3 polymatrices with these sums. And you need to rewrite this, not recite, in terms of 2 qubit gates. So let me correct that. So here's a trick. This is a trick that I learned by reading papers. If you take the following 2 qubit plaquette exponential to the I alpha, sigma 1 tensor 1 minus sigma 2 tensor sigma 2 cross 1, the first and the second one in the sandwich commute with each other. So I can write them inside the same exponential. And then if you conjugate with this sigma 3 cross sigma 2 pi quarters rotation, what that basically does is a sigma 2 dependent rotation in the third variable in the sigma 3. And if you do the algebra, which takes a bit, you can show that it generates the 3 qubit gate that we have in the top, the exponential to the I alpha, sigma 2 cross sigma 2, and then minus sigma 1 and various other things like that. And you see that you generate part of the plaquette that we needed. You can do the same with a different combination of sigma 1, sigma 2, and sigma 2, sigma 1. These 2 terms inside the middle one also commute with each other, so there's no particular order in which they need to be done. And again, you have a pi quarters rotation with a different 2 qubit gate for the sigma 3 and sigma 1, and you generate another piece of the interaction. And then one of the nice things about writing it in this way, which is not obvious, is that all these parts of polymatrices actually commute with each other. So there's if you have 3 1s and you have a 1 and 2 2s, the sigma 1 and sigma 2 anti-commute, but there's 2 1s and 2 2s, so you get 2 minus signs. So you actually get that they all commute. So they all commute, so because they commute, when you put them together, if you have a perfect quantum machine that generates these interactions, you generate something that generates the correct plaquette that did not spoil the gauge invariance. Okay. And then to show you that I learned something about quantum computers, this is how you write it. The two-gate quantum system that produces the XX can be written in terms of the ZZ gate, which is usually called the Ising gate, which is the one that's usually provided by single qubit rotations with pi halves in various directions. And all of these things, I've been told, you get implemented. Okay, once you have a triangle, you assemble the triangles and you evaluate them in a checkerboard pattern, meaning black then white or blue then white. So you need about 15 to 20 consecutive gate operations per qubit per trotter step on a single triangle. And then if you double this, you basically run out of time on your computer. Okay, here's a statement about how you evaluate things. You take the Hamiltonian I showed you and you try to fit parameters so you're close to the maximal spin symmetry. And then what you do is you just tune the electric field close to the XXX Hamiltonian so the splitting is small. So you don't get too far from that. So the states we want are here. This is what perturbation theory will tell you. And then you do the same with the plaquette terms. What's the conclusion? The conclusion is that the ingredients for gauge theory calculation are there for finite resources, not too many qubits per link, not too many gates per qubit. The architecture assumptions for setup are that the success will depend on the details, but the architectures that are there are good for lattice gauge theory in that you have qubits with nearest neighbor interactions. And the advantage of local quantum field theory is that local quantum physics is about local degrees of freedom interacting with their nearest neighbors. So in a certain sense, the architecture that we can build or that they can build for these machines is kind of the right choice for a lot of the questions that we would like to do in gauge theories. We can in principle initialize this to zero electric field plus random assortment of plaquette actions on reference state, which is the electric field, equal to 0. So we could in principle study some gauge invariant states as an initial condition, can evolve for some time, and in principle avoid these bad states. And what I want to tell you is that if you think about this as how did we get to this Hamiltonian, we were doing a physics approach, which was basically using angular momentum ideas rather than a brute force computer science digitalization approach where you just say, well, I need the states from -5 to 5, and I'm going to do a brute force digitization of that into a Hilbert space of qubits. We probably waste more memory, but we gain on the number of gates. The jury is still out in that we need to wait to see what happens when we actually run it on the machines, but we're getting there. The goal is to now go and put it in these machines and check the error rates, etc. How long can we make the trotter steps? And then running out of time is a big issue, and I just ran out of time. Okay, that's it.
Thank you very much, David.
Okay.
Very nice talk. So are there any questions? I think there are 2 questions in the chat. Would you like to ask the questions, each one of you, or should I read them? Felipe, would you like to ask your question? Okay, I don't think so. So I'll read it. In hadron QCD reactions, we need superposition of wave functions in different reference frames to represent, for example, a form factor. It is not enough to have the Hamiltonian implemented. One would also need the rest of the Poincaré algebra boost operators. Has this been looked into?
Okay, so if you actually want full relativistic field theory, there's a problem which always shows up, which is that the unitary representations of the Lorentz group are all infinite dimensional. So you will never get the boost operators. What you hope to get is the low energy physics up to some scale, and then hope that that's good enough. So if we do a form factor for QCD, the ones that are interesting will be the ones of the low energy physics of QCD, like slow nuclear reactions. If we want to do very high energy physics, eventually Parton distribution functions will be ideal, but this is beyond what the current quantum computers can do. Once you have Parton distribution functions at some intermediate scale, perturbative QCD can be used to generate the rest of the information going upwards, like it's done in big accelerators. So where we need the most information is actually at low energies, like how do you compute the mass of the proton, or how does the proton interact with pions at low energies, or other things like that. People can do this for simple setups in QCD, but they cannot do it for the helium atom, for example. So understanding how the hydrogen binds into the helium atom would be beyond what people can do, and this requires, hopefully, this type of information. Now, let me give you the bad news. The bad news is that QCD has a big group. It's SU3, it has 8 generators. If you start looking at the dimensions of the representations of QCD, you very quickly run into big numbers. So the number of qubits that you need per link is large, and then you run out of a quantum computer before you even have a plaquette, let alone a volume of QCD. Once we get into the numbers of thousands of qubits, then maybe we'll be able to do something serious about QCD. The reason why they do 1 in 2 + 1 dimensions is really to try to understand which algorithms are going to be the best ones long-term. And hopefully, and this is a hope, we'll tell the people who build the quantum computers what are the best gates to have around with high fidelity. Okay?
Okay. Thanks, David. Andres, would you like to ask your question?
Yes, thank you, Carlos. Thank you, David, for your nice presentation. I have 2 questions. The first one is, what is the relation among tensor networks, gauge theories, and quantum computing? Can the renormalization group help or say something on modeling gauge theories as quantum processes?
So tensor networks are a particular type of ansatz to build wave functions for lattice systems. Okay. Some of them use tensors that are built of unitaries, and in principle could be implemented on a quantum computer after proper initialization. People have been talking about that. So that would be something that would set the initial conditions. So if you can generate that, you'll be able to generate some initial conditions on the system. If you generate a ground state, it's not a very interesting initial condition because nothing happens when you apply the Hamiltonian to it. So the idea is that once you have this ground state, hopefully you will be able to act on it to generate excitations and then see what they do in real time. But there are different approaches to understanding physics. And a lot of the work that people do on tensor networks is really about finding ground states of condensed matter systems. Mostly because if they do it with classical computers, they run out of space otherwise. Okay.
Okay.
Can the renormalization group help or say something? Hopefully, yes. We still don't know very well how to do renormalization group in these kind of gauge theory lattices for real-time physics. Usually there would be some sort of blocking algorithm, but we don't know how that works yet.
Okay.
Okay.
Thank you. Thank you.
Okay, there's another one from Jairo Alexis Rodriguez. Is it possible to implement the Feynman path integrals formulation in quantum computers?
It can be done directly, but it's kind of computationally intensive. If you do a naive path integral, that would mean that you would need to change between position and momentum representation time and again. That's how the path integral usually works. To go from position to momentum, you need to do a Fourier transform. If you do it in quantum systems, you would need quantum Fourier transforms. But the idea is that we know that the path integral and the Hamiltonian evolution of quantum systems are equivalent. So if you can implement the Hamiltonian evolution, it is faster than the path integral from the point of view of the numerical operations that you would need to do. And then the physics is the same, so might as well do it in the Hamiltonian formalism. This is in some sense because the system is a quantum Hilbert space, and the natural way to act on Hilbert space is by unitaries. It turns out that quantum computers are ideally suited for Hamiltonian problems rather than the more kind of path integral Monte Carlo type setup, but they are essentially equivalent. Okay, now there's another question from Gabi. Okay, so it's about boundary conditions. So boundary conditions are important. If you're doing lattice gauge theory for QCD or anything interesting, the first thing I would do is put periodic boundary conditions. And then there will be some finite volume effects that you need to understand. So you need to change how big the lattice is and understand what the lattice or what the boundary condition, the finite scaling, the finite volume effects are, and then extrapolate to the infinite volume. They always enter, they give rise to Casimir effects, they change various energies of states just due to the confinement that they produce, the additional confinement due to finite volume. But at least in principle, they can be taken care of if the lattice is big enough. And then one can extrapolate to infinite volume that way. Yeah, they always enter. In this case, they'll generate energy shifts on the interesting states, and some of the dynamics might be polluted by finite volume effects. Okay, any other questions?
Okay, apparently not. Thank you very much, David. Very nice talk.
Okay, thank you all.
Okay, so let's continue. So we will now hear the final talk of this opening session. We'll hear from Reina Camacho about the Higgs boson. Reina is a Venezuelan particle physicist. She works in Atlas since 2009. And she currently works at the French National Research Center and the University of Paris. So Reina, thank you very much for accepting our invitation, and please go ahead.
No, thanks to you for the invitation. It's very nice to see these kind of spaces, even during COVID time, to talk about physics and share the latest results from our research. Okay. So can you please confirm that you can see the slides?
Yes, we can see it.
Okay, perfect. So as Carlos mentioned, I will be discussing the Higgs physics in the Large Hadron Collider, the status and the prospects. Just a disclaimer, this is a personal and biased selection of the results. As I will mention at some point during the talk, there are hundreds of papers and analyses studying this discover Higgs boson. And another disclaimer is that this will be an experimental view or review of results mostly. So what I will do first is to introduce our main tool, which is the Large Hadron Collider. And then I will divide the talk in 3 parts. So first, I will tell you the story that brings us to the discovery of the Higgs. Very short. The second part, I will discuss the current status, the latest results that we have from the Large Hadron Collider. And finally, I will discuss in the third part the prospects. So the Large Hadron Collider, or the LHC, as you may know, is a proton-proton collider of 27 kilometers circumference that is situated at CERN in the border between France and Switzerland, and is currently running at a center of mass energy collision of protons of 13 TeV since 2015. Although we are taking data since longer, so we start actually taking data in 2010 steadily. So we have several main detectors, but here I'm just showing 2 of them, CMS and Atlas, and just because those are the main key players when we are talking about Higgs physics. Okay, these 2 particular detectors, they are non-specialized detectors in the sense that they were designed in order to study a very broad range of physics. They are based in the same concept, but they use completely different technology, which is great because then we can actually compare, and if we discover something new in one of the experiments, it can independently be confirmed by the other one. So what other characteristics of these detectors? So we have an excellent vertex and tracking system, which is very important in order to measure the kinematics of charged particles, like for example, measuring the transfer momentum. We have a large coverage for muon detection, and we have an excellent calorimetry, or 2 excellent calorimeters in each one of the detectors with very large coverage. And calorimetry is super important in order to measure the energy of the neutral and the charged particles. Okay. So Higgs boson. The Higgs boson was discovered in 2012. It was largely covered by the media at that point. So here you can see a picture that was taken at CERN during the announcement of the discovery of this particle. In the picture, actually, you can see the 2 spokespersons of the experiments, Atlas and CMS. So you have Fabiola Gianotti, who was the spokesperson of Atlas, of the Atlas experiment at that point, and currently she is the director of CERN. And on the right side, you have Josephine Candela, who was the spokesperson of CMS at that point. So since then, since 2012, we have come quite a long way. When we are looking for Higgs boson and results about the Higgs boson, we can find more than like hundreds of papers since 2012. So here, just if you want to dig a little bit more deeper into these results, I just put the 2 links to the Atlas public page for Higgs results and the CMS public page also for Higgs results. And it actually also came with a Nobel Prize in Physics in 2013 that was granted to François Engler and Peter Higgs for the theoretical discovery of mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the Atlas and the CMS experiment at the CERN Large Hadron Collider. So already a few key points. This particle is related with the origin of mass of subatomic particles. So exactly what it is and why do we care about the Higgs? Why we continue talking about this discovery 8 years after that? So we are talking about the discovery in 2012, and still today there are so many things that we are learning about these particles. So why exactly do we care about this? So the Higgs boson was the main ingredient, like the missing ingredient for the standard model, which you know is a model that basically describes the interaction between the smallest components of matter, or at least the smallest that we know so far. And it has been like very, very successful from the experimental point of view. So let's put ourselves a little bit back on time in the 1975, and let's see what was the particle physics world at that point. So at that point, we have a standard model that was a standard model theory that was based on a local gauge symmetry. So basically, we have the SU3, SU2, U1. So SU3 describing QCD, SU2, U1 describing everything that was related with electroweak forces. The group representation was determining the interaction form. So leptons were SU3 singles, they don't interact strongly. Quarks, SU3 triples, interact with gluons. And then you have left fermions who were SU2 doubles, interact weakly. Right fermions, singles that do not interact weakly. And at that point, we didn't have, or the model didn't predict mass term for fermions, and also no mass term for the bosons W and Z. But surprise, surprise, in 1983, two experiments, the underground area 1 and underground area 2 experiment, announced the discovery of a massive W boson. So we needed to patch somehow this model, and the standard model solution to the mass problem came in two ways. So from one side, we added a scalar field with a spontaneous symmetry breaking in order to give masses from the theoretical point of view to the W and to the Z to fit what we were observing actually experimentally. And actually the Higgs boson is the experimental proof of the existence of this scalar field. On the other hand, in order to give masses to the fermion, there was the addition of the Yukawa couplings. So this is a discovery that was a very important milestone for high energy physics in general. So here you can see the excitement that there was in the at CERN, actually the day of the announcement of the discovery. So here you can see actually Engler, who was one of the person. Actually, there were two groups that proposed the existence of the Higgs field, and Engler was part of he won the Nobel Prize in 2013. So many people wanted actually to be present in that announcement. Actually, the queue was huge since the morning. People sleeping the day before outside of the room where this discovery was announced. Now, as high energy physicists, we want to know the most intimate secrets of this particle. We want to know if the standard model Lagrangian structure is correct. We want to know if the values of the couplings of this particle with the other fundamental, with the other particles of the standard models are the ones, if those values of couplings are the one predicted by the standard model or not. We want to know the shape of the Higgs potential. We're interested in all this. And this is why after the discovery, until now, we have been doing several measurements in order to give answers to these questions. But it's also the existence of the Higgs, this particular discovery and everything related with the study of Higgs physics is also important for science in general, as the knowledge of the values of the Higgs coupling is essential to understand the deep structure of matter. So we know that or according to the standard model, the Higgs couples to W and Z bosons. It couples to fermions via the Yukawa couplings. And in that sense, we have that the Yukawa up and down quarks are related with the stability of the nuclei. The electron Yukawa is related to the size of atoms. The top Yukawa decides partly the stability of the electroweak vacuum. But the Higgs also couples to itself via itself, and it controls the thermodynamic of the electroweak phase transition. So when I'm talking about the results, you will be basically listening to the latest result regarding these couples. I mean, what have we discovered so far regarding these couplings? So the standard model included this scalar field and the existence of the Higgs boson, but it was not kind enough that it didn't tell us which mass should have that particle. It said it should exist. We don't know which mass it could have. So that's why this free parameter was one of the things that we didn't know when the LHC started, or we didn't know for sure. But there were some constraints on the mass or where the mass of the Higgs should be due to indirect constraints from other electroweak processes measurements. So it was discovered in 2012. It took a while. The Higgs mechanism was proposed in 1964. LHC was approved by CERN Council in 1994. The LHC civil engineering work started in 1997, and the commissioning of this accelerator started in 2008. It was in September 2008 when we had the first beams, but it was also at that point that we had an accident with the superconducting dipoles. So it was not until 2010 that we actually had useful beams that we could use, data that we could use. Very quickly, with the data set of 2010, 2011, the two experiments, the two collaborations, Atlas and CMS, they excluded the existence of a standard model Higgs in a very large mass range, spanning up to 600 GeV, with the exception of a very narrow window around 125 GeV. And this was actually the place where finally, after analyzing the data set taken up to then, 2012, we could announce the discovery, meaning that we had enough data, such as the discovery or the existence of this particle that we were observing was statistically significant. So we use the data set collected between 2010 and 2012. This is what we call run one. So this is this first phase of data taking of the LHC. At that moment, the energy at the collision point between the proton was 7 at the beginning of the run and 8 towards the end of the run. And we collected 30 inverse femtobar. So this is what you see here. And by an inverse femtobar, this is a measure, like an inverse femtobar, this unit is a measure of the amount of data collected. One inverse femtobar corresponds to 10 to the 12 proton-proton collisions. And we use this in order to translate the cross-section of a production of a process into a total number of events. So I mentioned that one inverse femtobar was 10 to the 12 proton-proton collisions, but there are so many processes that happen that are produced at the LHC. It's not like these 10 to the 12 proton-proton collisions are just Higgs, okay? There are several processes. So in order to understand how the Higgs was observed, we need to take into account two things or two main information: how they are produced and how they decay. Because a Higgs is not just produced and we can see the Higgs going through our detector. Actually, the Higgs decays to other particles. So it makes quite challenging the observation of these particles. So how is the Higgs boson produced at the LHC? So there are mainly 4 production modes. We have one that is called gluon-gluon fusion, where we have just a Higgs in the final state. This is actually the main production mode at the LHC. It has the highest cross-section. It also suffers most of the time for very large backgrounds. That means other processes that have a final state, a topology in the detector that is very similar to the signal that we want to see. The second production mode is the vector boson fusion, or BBF for short. And here you see the Higgs that is produced with two other quarks that we see in our detector as jets. And these two quarks has a very high rapidity separation. So it's a very characteristic final state, very characteristic topology that we can observe in the detector. It helps improving the triggering, and it helps with the rejecting the background or other processes that could emulate this topology. The third is the production of a Higgs in association with another boson, either a W or a Z. In this case, most of the time, so far, the analysis that has been done trigger this particular topology using the electronic decays of the W or the Z boson. And it's particularly interesting and important because this production mode gives us access to the Gauss coupling, so the coupling of the Higgs with the W and the Z. The third production mode is the association of the Higgs with two top quarks. Usually, most of the analysis that we are doing, not all of them, but most of them use a semi-electronic decay of the top in order to trigger or to trigger this particular final state. And it's very important because it gives us access to the top Yukawa coupling. But this is not the whole story. We need to know how it is produced, but we need to know actually also how the Higgs decay in order to understand what final state, what topology we are looking into our detector. So when we're talking about the decay, probably you are asking, what is the best decay to look for such a particle? The Higgs can decay into several combination of particles. Actually, before knowing that the mass of the Higgs was 125, what we had was a branching radiation plot telling us what were the percentage of the branching radiation of the decays as a function of the mass. So now that we know that the mass of the Higgs is 125, the dominant decay mode for the Higgs is 2B quarks. So we have the Higgs that immediately decays to 2B quarks. So at the end, what we're looking in our detector are two jets that are coming from a B. This is 50% of the branching ratio. So 50% of the time, the Higgs decays to 2B quarks. It suffers usually with huge backgrounds coming from QCD or multi-jets. We also have the WW decay, which is make up more or less 22% of the decays of the Higgs, but the reconstruction of this particular decay is incomplete because the W decays to a lepton and a neutrino, and the neutrino we cannot detect it in our detectors actually. Then we have other decays that are smaller. We have the ZZ, which is very clean, is fully reconstructed, but it's a small branching ratio. We have the Higgs, which have even a smaller branching ratio, so you can see it here. It has a lot of background coming from QCD, from photons and from QCD jets. It's a final state that can be fully reconstructed, and it's a very clean mass measurement. And then we have the decays to the tau, which make up more or less 6% of the decay, and it has also an incomplete reconstruction most of the time. But if you look at this, you will say, okay, maybe I'm sure that the most easy thing is to go and look to the Higgs into the BB final, in the BB decay, because we have so many of them. But actually, no, there is an interplay between the production and the decay based on the kind of backgrounds that we have. And to be honest, these interplays tell us, for example, that when we are looking into the Higgs to gamma-gamma, or the Higgs decaying to ZZ, or the Higgs decaying to WW, the easiest thing in terms of background is to look at these topologies when the Higgs is produced in gluon-gluon fusion. In the case of the tau, the two main production modes that we have studied is the vector boson fusion and also the gluon-gluon fusion. In the case of the Higgs 2BB, the main production modes that we have looked at so far is the associated production with a pair of tops, or the associated production with a W and a Z. And surprise, the first decays of the Higgs that were observed was not the BB. Like, we could think, okay, there are so many of BB that is easy. But no, actually, the decays of ZZ in WW or gamma gamma or photon or two photons were the first one to be observed. Because even if the branching ratios for these are smaller than for other decays, the reconstruction of this final state in our detector was easier. It was easier actually to disentangle this signal from the amount of background that we have. It was a very clean reconstruction. So these were the three main decays that were used for the discovering back in 2012. And actually, with all the more data that we have been collecting since then, we are now actually doing precision measurements with them. We went from the phase of discovery, it is there, we have seen it, to the phase of doing precision measurements with these three particular channels. So here in the plot, you can see the invariant mass of two diphotons in the experiment. In this case, this is data from Atlas, from the Atlas experiment, and you can see the shape. Well, you can see the data in the black dots. You can see a fit to the background that we have, and you can see the signal. So with this peak appearing in the invariant mass of the photon around 125, and you can see a similar plot in this case for the ZZ decay that each set goes to 2 leptons. So basically you have here the invariant mass of 4 leptons, and you see around 125, the mass of the Higgs. You can see the signal of the Higgs appearing in this case. So this was 2012. Where are we now? Where are we today? So the round one finished in 2012. Then we had a period of a couple of years in a long shutdown. It was a period for maintenance of the accelerators and the detectors. And then in 2015, we started the second phase of data collection, what we call round two. It lasted until end of 2018. So it lasted 3 years, a little bit more, 2015, 2018. There was an increase in the energy from round one. So as I mentioned, in round one, the proton-protons were colliding at a center of mass energy of 8 TeV. In round two, we increased this energy collision up to 13 TeV. And we collected 140 inverse femtobar more on top of what we already have in round one. It's a large increase in integrated luminosity versus time. There were also a lot of improvement from the teams and the collaborations and the analysis on the performance, meaning how well we are reconstructing the particles, how well we are reconstructing the ogens, the electrons, the muons, the B quarks, how well we are reconstructing those in our detectors, and also in the methodologies used in the analysis. For example, right now, even more and more we use machine learning techniques in our analysis. All this actually made a lot of progress in the last few years. So I mentioned at the beginning the observation of the Higgs was in 3 channels. Today, in the last few years, there are many more decays and production mode that has been observed. So we are little by little putting the pieces together to understand and to kind of have an identity, an ID for the Higgs. So for example, using the 2016 data, we could observe the decay of the Higgs into 2 tau leptons. Using the data set, partial data set of round 2, We could observe the Higgs decay into BB. This was announced in 2018. We could observe the TTH production, so the associated production of a Higgs with two tops, combining different decay modes. And there is an evidence of the existence of Higgs to decay into two muons. Evidence, so still not observation, but we're getting close. So there is a large sample that we have collected of Higgs bosons in the RON2. There are more or less 8 million of Higgs boson that has been produced and has been collected in our data set per experiment, so per ATLAS and CMS. And the analyses are in different stages. So we have, as I mentioned, we have already some analyses that are in the precision stage. So we are measuring more precisely the spectra of the transport momentum of these decays. And this is the case of the initial discovery channel, let's call it, to photons, WWs, etc., even the tau-tau. We have other analysis like the BB decay that was recently observed, and we are just like now starting to do some precision measurement, but we also have some of them that are in the search phase. We still have not observed them. And these are the decays of the Higgs going to 2 quarks C, charm quarks, or to 2 muons, or also the process of the di-Higgs, which tell us something about the potential, the shape of the potential of the Higgs field and the self-coupling of the Higgs to itself. So what I want to do in the second part is to highlight a few recent results, state-of-the-art, most of them using full RON2 data sets, so the data that we have collected between 2015 and 18. Just to mention that we are still in the phase of updating some of these analyses using the full data set. So many analyses or many more results can be expected in the next few months. I just wanted to mention how the community of doing Higgs physics is coming together. Also in COVID time, we recently have one of the major conference in this particular area that is called Higgs, and it was 1 week conference, 87 talks, more than 1,000 people connected. Like now we are. So it's a collaboration. It's a team of people that is very active on trying to understand the physics of the Higgs boson. So let's start with the precision side. What are the news regarding full RON2 results on the precision side? Well, we recently have one result, the one that you see at the left side, using the set decay of the Higgs by ATLAS full RON2 dataset, and it's very impressive that now the mass measurement is at the level of the precision of the mass that we are measuring is at the level of 0.1%. Still, the statistical uncertainties are leading, and the main systematics that we have for this particular analysis is the scale of the muon reconstructed in the experiment, in the detector. So here you can see the invariant mass of the 4 leptons, so 2 leptons coming from each set boson. And another result that is very important to mention is a CMS result using the decay of the Higgs into 2 tau that managed to measure the CP mixing angle, also using the full RON2 dataset, and it constrained this angle to 4 plus or minus 17 degree. This implies a rejection of the CP-odd components to coupling with fermions of more than 3 sigma. Couple more results that are important to highlight is the vast program of kinematic measurements that we have when we're talking about the Higgs. So far, now in 2020, we have observed the all five main production modes of the Higgs, 4 main production modes of the Higgs. We are actually now measuring differential cross-sections. So the cross-section not as a global quantity, but as a function of some quantities like the transfer momentums of the Higgs. And there are several measurements by production mode also in various kinematic regions. This is called STXX. So you can see here, for example, the cross-section times the branching ratio for the Higgs in different production modes and in different regions of transfer momentum, for example. And so far, within the precision that we can see, the agreement between what we measure with the data and what is predicted by the standard model is quite good. It's very good, actually. So let's move from the precision to those modes that has been just recently observed. So here we have 2 of them. So on one side we have a decay, which is the Higgs decaying to BB. It was recently published, the results using the full run-2 data set, and we observe this decay with a significance of 6.7 sigma. The CMS experiment also observed it in this observed this decay, combining the data set of 2017 plus the data set that was collected in round 1. So here you can see in red how it looks like the Higgs to BB signal. And on the other side, we recently actually observed the production mode of the Higgs, the TTH production mode. It was observed in 2018 with a significance of 5.2 observed by CMS and 6.3 observed by Atlas. Now, this was in 2018, and now with all the processing, the whole data set of round 2, we are even observing some of the individual decays. So not just the full TTH production, like combining several decays, but already we have observed the TTH going in a particular channel, which is Higgs to gamma gamma, and this is what the distribution that you have here at the bottom right is the invariant mass of 2 photons in production mode that is TTH, and you can see clearly the signal of the Higgs around 125 coming out from the background. Now on the search side, there are a few things that we still don't know about the Higgs. In particular, with respect to the couplings of the Higgs with some of the 2nd generation particles. These are particularly challenging because they have a small coupling in the standard model, and they also suffer from a large background. So on one side, we have a search that is ongoing of the Higgs decay into 2 muons. The most recent results has shown an evidence of the existence of this channel, but not an observation yet. So by evidence, we mean a significance of more than 3 sigma. By observation is more than 5. But so far, the results that we have obtained from this search are consistent with the standard model prediction. Now, another search that is ongoing is the search of the decay channel of the Higgs going to CC, 2 C quarks. And here you can see an upper limit on the signal strength. It's a very, very challenging channel to observe. The best option that we have to observe it is using the VH production mode, but tagging CJET is quite challenging in our detector. There's a lot of background also for this channel. So these are, for example, 2 of the analyses that we are looking forward to see what will come out regarding prospect, what will happen in the future when we have more data, for example. The other important search that is ongoing is the the di-Higgs production, because the di-Higgs production, the production of, is, you can see the diagram here, the di-Higgs production is directly related to the self-coupling term. So the link or the self-coupling of the Higgs to the Higgs. And this tells us information, this gives us information about the potential, the Higgs potential. This is a very rare process in the standard model. Actually, the cross-section of the di-Higgs production is 0.1% of the cross-section of the gluon-gluon fusion production. So just to give you an idea of how rare the process is. And there are several searches taking into account different decays of the two Higgs in the di-Higgs production. We can see that the most promising ones are when we are looking into BB, like 4B production, or gamma-gamma BB. Those are most of the searches that are been taking place. So here you have the most recent result of the Higgs production, double Higgs production. One of the Higgs decay into 2 photons, the other one decay into 2 bits. And we have a current limit, the best current limit of the cross-section times production branching fraction is 7.7 times the standard model. So the Higgs boson so far, this 125 Higgs boson that was discovered and we have been measured so far, shows quite a good compatibility with the standard model. If we look at the signal strength, the most recent combination from Atlas and CMS is very close to 1. So this tells us, the closest to 1 tell us the compatibility with the standard model. If we look at the couplings to weak bosons of the Higgs, they are consistent within 5% with the standard model. We have observed the Yukawa coupling for top, for bottom, and tau fermions already. The spin zero nature of this particle was also confirmed in round 1. But there are still some phase spaces, there are still some measurements, there are still some possibilities within the study of the Higgs physics to look for new physics, to look for physics beyond standard model, things that are not contained or explained in the standard model. For example, if we measure the property of the Higgs with better precision in corners of the phase space, this is one way of using the Higgs as a tool for new physics, searching for Higgs decays to non-standard model particles. So there are many analyses ongoing looking for Higgs decaying to dark matter particles or Higgs decaying to long-lived particles, things that are not predicted, that are not included in the standard model. Or there are also many theories that predict the existence of new physics that contributes to already standard model processes. So for example, when we are looking at the di-Higgs process, there are theory of extra dimensions or 2 Higgs double models that add additional contributions to this process, to the di-Higgs process. So the better, the more precise measurement we do, the easier will be actually to corner the presence of new physics or physics beyond the standard model. So here I will go very quickly through this. It's just a snapshot of some of the analysis that use the Higgs boson as a tool to search for new physics. We can come back to this if you're interested during the question time. So how do we do in order to know more about this? What are the prospects of the Higgs boson? Well, the first thing, it will be great to have more data, which is good because it's coming. So right now, Atlas or the LHC is in a second shutdown. It's called the Long Shutdown 2. Is a period of maintenance and some upgrades also for the detectors. And then in 2022, we are expecting to start the third run of data collection. It's a 3-year run. We plan to run at 2 or 2.5 times the nominal luminosity. And there is a possibility of having a very modest increase on the energy For now, the start of the round 3 is delayed due to COVID. It was supposed to start in 2021, now has been shifted to 2022. And while we wait for this data set that will come, there is a lot of work for experimentalists and theorists to do. Actually, if we check the analysis that we have already done and the previous results, there are some of them that already are dominated by systematic uncertainties. So working on reducing the systematic uncertainties from theory, from modeling, from Monte Carlo, from PDF, is something that we are doing, that the theorists are doing. And from the experimental point of view, there is a lot of work ongoing in order to improve the performance of the detector and in order to improve the analysis techniques. So together, round 2 and round 3 will amount to more or less 350 or 400 inverse femtovar. And some measurements will clearly benefit from this. For example, the decay of the Higgs to muons is around the corner. So we think that combining round 2 and round 3, we could reach the observation at the end of round 3, combining ATLAS and CMS. Looking at the high energy, high transfer momentum regime with these additional statistics will also be a plus. Making global combinations is also something that we're working on. Having more data will allow us to access new phase spaces, we hope, in this search for new physics, in this search of understanding more about the Higgs. And after that, we have what is called the high luminosity LHC. So the high luminosity LHC will come after a third shutdown, that you can see here. During the high luminosity LHC, we call also the high luminosity LHC a Higgs factory, because we will have 170 millions of Higgs bosons that will be produced, and 120,000 pairs of Higgs boson. When we reach the total luminosity that we are expecting for the high luminosity LHC, the expectation is that it will manage to collect 3,000 inverse femtovar of data. So it's true, round 3 high luminosity LHC means more data, a little bit more of energy, hopefully, so we can go to 14 TeV in the collision, in the center of collision. We can access some rare processes, but it's also more challenging. It's much more challenging when we're increasing the luminosity. The reconstruction of the objects becomes very, very complicated. You can see, for example, here, the difference in the number of collisions that happen at the same time in the different runs. So round 1, so we usually have like 5, average of 5 collisions happening at the same time with all the particles that can be produced in each collision. Round 2, we have an average of 40. High luminosity LHC, we are talking about 200 collisions happening at the same time. With all the particles that come with that, it's a very challenging environment to understand exactly what is going on and what is being produced to disentangle the signal from all this background that we have here. So we need better detectors in order to do this, in order to make sure that we can profit and we can benefit from this data set that we will get in the high luminosity LHC. And this is why during the lot shutdown 3, that will be a phase in order to install upgraded detectors for ATLAS and CMS. So these upgrades are being built right now. Just to mention one of the examples of the upgrades that will be done in ATLAS, we will completely replace the tracking detector. The tracking detector allows us to measure the charged particles that are produced at the collision. It's super important in order to detect, to measure the electrons, muons. It's also very important to measure or to detect and to identify the jets that are coming from B quarks. So there will be a completely new inner detector that will be installed. There will be also new electronics. The trigger system, the data acquisition system will be upgraded. CMS is also developing right now and will install some changes in the calorimeters, in the immune system, also in the tracking, and a new timing detector. So high luminosity LHC will dramatically expand the Higgs physics region. We are talking about going from 315 femtobar at the end of round 3 to 3,000 in the whole data take period that will go until probably 2040 something. That means that with all these data sets, we expect there are estimations that we have done that tell us that we will be able to measure many of the Higgs couplings with a precision that goes between 2 and 4%. And at that point, as you can see here, you see here the couplings. These are predictions, of course. These are the couplings of the Higgs with the different particles and the expected uncertainty. You can see the statistical uncertainty, the experimental uncertainty, and the theory uncertainty. And we see that for some of them, actually, the theory uncertainty remains the largest component for most measurement. Again, these are predictions with the information that we have now, but we know that the experimental community and the theory community are working very hard. So this could be even better than the expectations that we have set so far. The other thing is that we expect that when we're talking about differential cross-sections, theory uncertainty will basically dominate all beams except at the high PT. Again, there is a lot of work being done right now, so we expect that we will surpass the predictions or the estimation that we have right now. Another process that we mentioned already is the self-coupling, the importance of the self-coupling in order to really understand the nature of the Higgs boson. And we expect that at the high luminosity LHC, the significance of the di-Higgs signal will be at the 4 sigma level in both experiments, with an uncertainty on the self-coupling of 50%, more or less. So you see, many of the things will improve. Already having a precision of 2-4% in some of the coupling will be great, but there are some processes that are much more difficult than others. Here is just an example, the di-Higgs. At the end of high luminosity LHC, we will have a 50% uncertainty on the di-Higgs production. So it's normal that we are thinking also even longer time scale than that. And the wish list beyond the high luminosity LHC is to be able to establish the Yukawa couplings to the light flavors. For this, we need precision, and to establish the self-coupling. And for this, we need high energy. So it was already mentioned at the beginning of the talk. Gabriela made a question about that, about the future, more beyond what LHC is able to do. And the community right now is making a big effort in order to understand what could be the next future, the next generation of collider. There are different colliders that has been proposed. They prove different dominant processes. Each one of them has their own experimental challenges. What we are able to do with each one of them is different. One of the things that we can say is that there are some complementarity between leptonic and hadronic colliders. This will be key in the future, but it's very difficult at this point to say what will happen. But there are a lot of effort in the community in order to understand what can be done in different scenarios. What can be done if we have an electron-positron collider overlapping with the high luminosity LHC? What can be done afterwards? Can we have another hadron collider like the LHC, but that can allow us to go to higher energies, or a muon collider, for example? So which machine will be? We will see. Again, there are several options. We can have hadrons or leptons. They complement each other. There can be a linear machine, or there can be a circular one. A circular allows us to go to have higher luminosity. We can have several interaction points. The linear is easy to upgrade. In energy is greener. There is less power consumption. So there are several scenarios that are being explored. And of course, many of them, as we can see here, this is a plot of the uncertainty that we estimate can be reached with different of these possible future colliders. And we see that for many of them, actually, we managed to get the couplings with an uncertainty or with a precision that is even below the 1%, which is very impressive. Okay, so this brings me to the conclusion. There are big progress on Higgs physics since its discovery in 2012. It's been already 8 years. These impressive results are due to great teams, collaborations, an amazing collaboration, taking data, making sure that the performance that we get with the detector is the best we can, due to technical improvement, due to the available data set that we have. All the measurements so far are in good agreement with the standard model prediction, given the current precision that we have. But there is still space for new physics. Unfortunately, there is no roadmap available for where to look for that new physics. It was different when the LHC was built. There was some kind of roadmap. Most of the people, they were convinced that the Higgs had to exist and that it was at the reach of the LHC energies. Right now, for the new physics, there is no roadmap to follow, so that makes it a little bit, that makes it challenging, that makes it also exciting. So right now there are more analyses in progress using the full run 2 statistics, the one that we have. And run 3 is starting very soon, do not forget that. The high luminosity LHC is a reality, it has been approved, it will happen. And we're evaluating also, the community, I mean, is evaluating updated scenario of proposed future colliders. We will see what will be learned in the next LHC runs and with high luminosity LHC, because hopefully those runs on the high luminosity LHC will provide new information about beyond standard model physics and the scale what that physics is, and that can guide us on the decision of which future machines can be built. Do not forget that there are also complementary and vibrant diversity programs worldwide, other particle detectors, smaller than LHC, but that also bring a lot of physics. So it's very important to keep that in mind also. And yeah, I'm very happy to discuss, to answer some questions. And I'm also very happy, again, as I mentioned at the beginning, to share these virtual spaces and bring the community together. Thank you.
Thank you very much, Reina, for this very nice talk. Are there any questions? Yes, so Gabi and Nicolas.
Okay, can you guys hear me?
Hi, Nicolas,
yep.
Yes.
Hey, thanks, Reina, for the super nice overview. So I have a question about the Higgs self-coupling. So are there, the results you present are about the trilinear coupling, but what about the quartic? I mean, I know they are related, but are there some searches for really measuring the quartic coupling and not the trilinear?
And not the trilinear. I'm not aware of searches like right now with the data set, but there are some estimations of what can be done in the high luminosity LHC for this.
Hi, Heine. Nice talk.
Hi, Gabi.
I was talking to a CMS researcher, and she told me that there will be some improvements on trackers and everything for the high luminosity LHC. I'd like to know if Atlas also having some development in detectors.
Yeah, actually, both of them. Let me just mention here. Yeah, so basically the tracking detector for Atlas will be fully replaced. There is right now a lot of R&D ongoing. Well, actually, we are already on the phase of pre-production for this, and the idea will be to have a all silicon tracker that will have a higher coverage than what we have right now. So it will go to the more forward region, so we can expand the region where we can do the measurements with the tracker. And there are other things. There are new muon chambers in the inner barrel region. There is also a high granularity timing detector that was approved very, very recently. And then on top of that, there are upgrades on the electronics and on the data acquisition system. And for CMS is more than the tracker. They also have several upgrades to other subdetectors, not only the tracker.
There are two questions in the chat. So is there a limit on Higgs to mu tau? And what is the current limit in the invisible decay?
So for mu tau, not aware of this of limits on these rare decays, but I'm happy to check and let you know, Diego. On the invisible, the best fit to invisible, the branching ratio is the one that you see here at the bottom. And the branching ratio smaller than 0.11 has been included at 95%. Those are the latest result.
There's another one. Are there any experimental prospects in the next run regarding the Higgs vacuum metastability, either in precision measurements in mass or for BSM physics?
Maybe who was the person? It was Andreas.
Yes, Andreas.
Andrea, I don't know if you want to maybe develop a bit more. If you can use your micro, of course.
Hi, yes.
Hi, Andrea.
Let me connect headphones so that you don't hear yourself a couple of times.
It's okay, actually. There is no echo. It's fine.
Okay. So yeah, I'm a theorist, so I'm working on this Higgs vacuum metastability topic, and I will be presenting on Thursday regarding our findings there. And I was just wondering, because I don't know that much from experiments. I just use the particle data group that they produce the review every couple of years, and we just use the values. But I was just curious if there is any prospects regarding, because there's a little bit of hit if the Higgs vacuum is metastable or if it is stable, and this has to do with the self-coupling if it turns negative after, let's say, 10 to the 10 GeV. So yeah, I was just wondering what is the feeling about this in the experimental point of view.
Okay, remember that for even at high luminosity LHC, the uncertainty that we will have on the self-coupling is 50%, so it's quite large. So it might be something that is being explored in future colliders beyond high luminosity LHC, where the precision can actually allow you to tell something about this. I'm happy to check and and come back to you if I found something. And I will be very interested in seeing your talk also, see what you're doing.
So yeah, I think from like what you see in the theorist's perspective is there's this top quark uncertainties that are quoted. So depending on how heavy or light the quark is, it can potentially stabilize the vacuum or not. And that's why a lot of people, depending on who you ask, who you speak to, some people say it's safe for the vacuum to be within the stability because the sigma deviation in the measurements still allow you to do that. But other people are less optimistic and they believe that the Higgs vacuum is actually residing in the metastable area. And again, depending on who you talk to about this, may be optimistic that any BSM or new resonances that you will be able to observe in the LHC will either help demystify what is going on or provide an explanation, or maybe it will take this metastability issue completely out of the way and it will just prove that the Higgs is actually very stable. So yeah, this is the type of questions that I get at the end of my talks, like, and because I'm not an experimentalist, I just wanted to see what experimentalists think about this.
Yeah, definitely.
Okay. Are there any other questions? Okay. Well, if not, I think we can close this session. Thank you very much, Reina, and thank you very much, everyone who participated. We will start again at 3 p.m. This afternoon. See you all then.